Today, he will deliver his talk on new development in nanotechnology. Sir, please start your talk.
Can you see the screen okay?
Yes, it's okay.
Okay. All right. First of all, Assalamu alaikum. And thank you very much for inviting me to give this talk. And I particularly want to first thank you, Dr. Kiani. And also I want to thank Dr. Salma and Dr. Anjum. I'm sure they have something to do with my name being in this conference. They were very nice students who worked in my lab extensively. So I thought I would take this opportunity and tell you a little bit about nanotechnology, something that is relevant to Pakistan and Pakistani issues. Of course, I can show you 200 images of really incredible work that is being done with nanotechnology in the fields of electronics, in the fields of medicine, you name it, and they have something going on in that area. But I thought that maybe it's time that we look at it more of its relevancy to Pakistan. So I kind of molded my talk according to that. Before we go to the current era, we need to look back a little bit, and I won't go into too many details of that. I have a full talk at some point, if you like. I can talk about the history of nanotechnology that actually extended back down to the pharaohs of Egypt, about 3,500 years. But I thought this is interesting because we all know about nanotubes and the existence of nanotube in this particular steel that was made in Andhra Pradesh and then exported all over the world, but in particular in the Arab world, where in Damascus, they used that steel in order to make swords. And they were very famous swords of that time. They were called the Damascus swords. So a lot of Muslims and especially the forces used that sword because of this super plastic properties that they had. And recently, meaning a while ago, 2006, a group from Texas analyzed the structure of these steels and found out that indeed there are nanotubes in that steel that gives it the plasticity or the superplasticity that it had, and that gives it the strength and yet the hardness. So when you talk about strength, certainly the brittleness comes to be an issue, but nanotube is one of the things that can give you the strength and the hardness at the same time. So they were very famous for these nanotubes. I'm gonna just turn my timer on so I know where I am. Okay. So from there we go to another example of Muslim use of nanotechnology, which is in the red ceramics that were very famous of their time from the Muslim Spain, especially in Granada. And all this red came from gold nanoparticles. And therefore the color has been very stable, for hundreds of years. And not only that, this whole area is of quite interest of the use of nanotechnology, the Mesopotamia, but not just the Mesopotamia that you're looking at. If you go to the right, go to the Central Asian countries, you'll see a lot of use of nanotechnology from way back when. When they don't know what they're using was nano in structure because there was no way for them to analyze it, but they knew the properties of these materials and they utilized those properties. One of the things that completely shocked me was when I was in Uzbekistan, and I'll come back to this, but this is in Farghana, which we know very well in our from the subcontinent context. There are these green ceramics, and this is very famous from that area. And when I looked around and talked to people, and then looked at some of the reports that were done before on these ceramics, they're basically copper particles. They're 50 to 70 nanometer particle. And with the lead oxide glaze, they don't use that too much now. Most of these things are decorative now. You don't eat with these things. but they look so beautiful. So you buy them, put in your drawing room or somewhere in your house for decoration purposes. But incredible, color that is a result of the interaction of copper nanoparticles with the lead oxide that they use for glazing. So that copper oxide that form copper oxide, as you know, has green color. The patina. So this is 13th century art. And then, of course, this Shahnama Firdausi that we are very familiar with. This is the poetry that is written about the adventures of the king, particularly hunting adventures. This is all written with colloidal gold. And some of the recent studies on the colloidal gold suggest that these particles are close to 100 nanometers. So right around the boundary of where you get into the nanometer area. So all of these are quite interesting examples. And of course, all of these three people. My purpose is not to go over what they have accomplished, but they led us into the current era of nanotechnology. And current era of nanotechnology brought with it some really incredible examples of what they can do electronically, especially if you can overlap the wave functions of some of these atoms, like it is shown in here. There is Donnie Eigler's work from about 20 years ago, I think 25 years ago, when you have a coral of cobalt atom on copper 111 surface, and where you see this one atom here, because of the wave interference and interaction, you see the image of that on this spot. So this is a technology that now is used in quantum electronics very commonly. So something that was 22 years ago as a result of the new industrial revolution, nanotechnology revolution that started way back when. This is a work that I did a little while ago, just to show an example of another use of nanotechnology in bioindustry. These are stents. Stents are for removing these restrictions in your arteries. The problem with normal stents is that when you put that in, because they cause their own damage to the artery. So after a while, the body builds up new plaque there, and you have another issue with another restriction. So the thing to do was to somehow have a drug in those stents so that it can be given off periodically or slowly, so that these will last for 10, 20, 30, 40 years. So this is a project that I had with Boston Scientific, where we use some of I cannot describe the material completely because of some proprietary issues, but it is just a matter of looking at the nanostructures of these. These are metal. This is a metal. A coating on the base is all nickel, which is biocompatible. And this is the structure of the nanofilm that is on top of it. And that holds the drug. Heparin, for example. Heparin is a blood thinner, and it can hold that drug for a very long time and slowly elute the drug. So that's why they call drug-eluting stents. So another advantage of nanobiotechnology. So therefore, as you can see, that there are tons of examples that have come up in the last 20, 25 years that are as a result of the work in nanotechnology. And this is just a small example. And this is an old slide that the nanotechnology project that was organized by the U.S. government with one of the think tanks doesn't exist anymore. But so this is kind of old data. I can assure you there are more than 2,000 products in the market right now that utilize nanotechnology or nanomaterials in one way, shape, or form. But as you look at these materials, some may be relevant to what issues that we in Pakistan face, and some are totally irrelevant. If a tennis racket can hit the tennis ball hard, or if a tennis ball with a carbon buckyball inside can go faster, how does that change the life of a Pakistani? So what we need to do is to look at some technologies that might be relevant to what ails us, what are the problems that we are facing in Pakistan. So here are some things that you can see. This is the one on the left with the mask. Is I just picked it up a few hours ago about use of nanosilver in a mask because of the COVID social distancing and social formatting. So these are available right now. As you can see, these are about $10. So very few Pakistanis can afford these kind of luxuries. And on the right, there are several of these applications described. And this came from a paper that was actually talking about what happens to these nanomaterials that can come out of these applications, right? Like, for example, toothpaste has some silver. These are all related to silver nanoparticles. When you brush it and you throw it out, where does that go? Right? So it has some effect. And I'm not going to go into the environmental issues that are related to nanotechnology. There certainly are. They are navigable to some extent, but nevertheless, we cannot just completely ignore those. So all of these things. But again, if you look at this, I don't know how many of these products are relevant to use in Pakistan. So this is a sort of a relevancy index that we have for Pakistan. And our major issues are related to disease, certainly, and especially in today's context, the whole world is related to that. Food, how the nanotechnology sort of overlaps with the food issue. There are certainly very cool products that you can think about in terms of sensors and whatnot that are quite relevant to the food. Energy, of course, a lot of work has been done. I've done a lot of work in energy. I won't talk so much about energy today, maybe just one or two slides towards the end. But mostly the thing that I want to cover is water. Not too long ago, the government of Pakistan had issued this national water policy. This is early days of Imran Khan. Very important policy, very timely policy, but there are all kinds of issues that I will just very briefly touch on. I encourage everybody who's listening to this to read this, because this is our existence. This is our survival issue. While we are talking about all those floods in Karachi, Thar always goes, completely dry in some of the dry months, and they have famine and all those things. And about glacier melting and all of that scenarios that people are talking about. So something that we have to be very sensitive about and do something very as much as we can. So water scarcity issues, as you can see in the map on the right, not just a stress, but to a scarcity. And you have seen the numbers coming from southern Balochistan and western Sindh, how difficult those dry times are for those people. Almost every single year, hundreds of people die just because of that. So the availability of water and certainly the quality of water, both are issues that we have to face. As I have read many places that, in Pakistan, more than 100,000 children die because of the gastro issues that are related to bacteria and viruses. So that is something that we need to certainly pay a lot of attention to. So, and this water policy does address that, recognizes that, which is I think a good thing to start with. And they have identified 15 concerns, and that include everything that I have talked so far. The only problem is that when we look at the policy objectives, there's only one time in the whole report they talk about research. Only one time. Everything else is about adoption of technology. Whose technology are we adopting? Where are we getting this technology? And if we cannot generate these technology, is there a way that we can afford this technology? So all of these questions, something that this report doesn't, directly address. And I think that's one of the major drawbacks in it. It correctly identifies the problem, but the solutions are left to be desired. And the word adoption, as I've shown here, comes up many times. Adopt this, adopt that. Where are this coming from? So we have ways to get into that, right? As academicians, as researchers, we don't have to wait for the government to give us the go ahead. And unfortunately, they have to provide some sort of funding. But some of these technologies are so easily available and so easily attainable that I find it hard that some There are some people, there are some labs who are doing these kinds of work that I'm going to talk about, but I'm surprised that there's not more of that being done. These are all cheap technologies. I won't talk about anything that is beyond the scope of funds that are available in Pakistan right now. And I understand what is the shortage at the moment. So photocatalysis is an old word. Many designs, many applications have been proposed using semiconductor photocatalysis in nano oxides, particularly titanium dioxide. But titanium dioxide is just one oxide. There are several other things that one can think about in this context. But, and even though this is so mature, the whole technology and whole application, you can buy these things in the market, right? You can go and buy a filter that is made up of semiconductor titanium dioxide nanoparticles. But those are absolutely non-affordable the way they are marketed right now by anybody in Pakistan. But this is, the material is cheap, the technology is cheap, and the technology is mature. So why don't we take one extra step and look into this from the applications point of view? I have a design that gives a little pipette to use this material through which you can, drink bacteria-laden water, and it will not hurt you. But that design of pipette still costs $1 per pipette. It's reusable. Put it in the sun, it gets recharged. But $1 is still not affordable. What can we do in Pakistani context? Labor is cheap. Why don't we do that? Filtration is another one of those issues that is so easily accessible. This is a work that I did several years ago in ComSets in Islamabad. And the results are just absolutely wonderful. But again, there are some issues, whatever, I don't want to describe those, that just stop the work where it was. But this is not something unique to what happened in ComSets. These results or similar results are available elsewhere, and one can easily look into those and see what we can do about it. So one of the issues, so these are University of Delaware people working in Malawi for a water filter project that we have there. But the problem that we have is related to bacteria and viruses, right? Bacteria are micrometers, viruses are nanometers. So all of these things need to be somehow taken out. The industrial pollutant, agricultural pollutant, they're all there. And they can be dealt with the type of filters that I'm talking about right now. There are filters available right now to deal with all of those pollutants. In fact, there are city water companies that are using nanofilter, for example, right here, right? Reverse osmosis, as we know very well, many of the Middle Eastern countries use reverse osmosis to remove salt. It's an extremely energy intensive process, and we can't afford that. Nanofilters is also something that are available. You can buy those. Paris, for example, run off of these nanofilters for drinking water. But at the end of the day, they take the filter out, throw it away, put a new one in. And they are very expensive filters. They can afford it, we can't. But there are ways that we can get around and do something more economic and in a way that is totally available and doable in Pakistan. And this is the work that I was talking about. These are electrospun nanofilters. Electrospinning is not a very expensive or complicated technology. I know at least 5 or 6 different groups in Pakistan that have this capability, and to scale it up is not an issue at all. As I said, that there are people who are making this commercially, but at an extremely high cost that maybe France can afford it, but we can't. So this is the whole filter, and you can see the size. It's just for comparison purposes. And here's a test that we did. On the right is a solution with 60 nanometer titanium dioxide. The titanium dioxide was used as a sort of to look like the viruses particularly. viruses are in the nanometer sizes. And on the left is a solution that you see after the filtration through these filters. This is just a holder, nothing else. And these are the nano spun fibers that we produced in ComSets in Islamabad. And you can see just the thing. My desire was there was a nala that goes through ComSets. So I was gonna go get a bucket of water there and filter it and drink it in front of everybody, but we never got to do that. But this is a technology that is easily scalable, available, cheap, no technological issues, no import of heavy machinery or heavy equipment that people won't export to Pakistan. All you need is a high voltage power supply. We took a old X-ray machine that they had in Arshad Bhatti's lab and used that. And there was some other equipment that was available already there. There was work that is already being done there. So it could be easily implemented and used. Water collection is an issue, as I was talking about Thur and its problem with the lack of water. This is something that I have seen in Chile. I spent my sabbatical last year in Peru and in that part of South America. And Atacama Desert, just as soon as you go just a little bit south of Peru, everything dries up. It's just completely dry land after that, until you get to the southern tip of South America. So these are, so in the morning, just by diurnal cooling, night cooling, they have these nets that are made of polymers. And because of this cooling, when there is the whole Pacific Ocean right there, sorry, Atlantic Ocean right there. And the fog comes up the ocean and then hits these collecting screens, and the water then drifts down. There's a pipe here, and it collects the water here. You can collect up to 6 to 8 liters of water from each of these things, right? So 6 to 8, keep that number in mind, because I'm going to show you something that might be very interesting to compare to these things. So look at the size of it. I don't know if you can see it. They might be like 3 or 4 meter by 2 or 3 meter tall type of screens. What we suggested, use a process which is very well known, very well developed, thermoelectric process that, and the thermoelectric effect that most of you know very well is just because of the movement of the electron from a warm junction to cold junction. You can do the cooling here. You can do it in different metals, but most easily done in a device like that are made with the with semiconductors. Like titanium dioxide is a large bandgap semiconductor that can also easily be used in here. My desire is to eventually make something that has thermoelectric and a photovoltaic and a water collector built in the same device. But this is, and you can make all of those with titanium dioxide. So this is for cooling. The electricity comes directly from solar cells that are associated with these devices. You don't need anything extra to that. So this is the project that I did with the Hacettepe University in Turkey. And I was supposed to go there this summer also to finish some of the work associated with this project. We ran some samples, we ran some examples. For example, here you have a silicon that is uncoated silicon, and there you have a silicon that is completely coated with titanium dioxide silicon. When you cool it down, and again, requires very little energy, that all can be obtained from a cheap, very cheap, dirt cheap solar cell. So totally independent product. And you can collect a lot more water here on a titanium dioxide oxide coated silicon than you can through uncoated silicon. And this is part of the work that I was supposed to finish this summer, but unfortunately I didn't get to go, but I will eventually end up there and finish this off. Very simple project. And the beauty of that is that titanium dioxide is relatively cheap, $58 per 100 grams. But look at the surface area that you get. 1 gram of 5 nanometer titanium dioxide that are easily available have surface area of 500 meters square per gram. 500 meters square per gram, right? So what does that mean? If we look at, for example, a cricket ground, we're very familiar with cricket. cricket ground has about 15,000 meters square area. And I'm just very roughly speaking, I know there is no fixed dimensions to cricket ground, but on an average, it's about 15,000 meters square. All right, 15,000 meters square means you need 30 grams of 5 nanometer titanium dioxide to get that area. So imagine, and I'm kind of exaggerating here just to make the point, because these are nanoparticles, so they're a spherical particle, not a flat surface. But 30 grams, you can cover 3 cricket grounds with $58 worth of nanoparticles of titanium dioxide, surface area wise. So imagine what kind of efficiency we will have in terms of water capture and so on and so forth. So here's another example that is very easily available to Pakistan science and Pakistan people. Something to think about. I have about 7 minutes left. I want to say just a couple of things about nanotechnology and energy. And I wasn't going to talk about this, but something happened that kind of clicked, and I said that I got to say something about it. I got an email from somebody in Pakistan. We don't have to name or the institute or anything like that. They wanted me to do a project with the student of theirs on polymer solar cells. Polymer solar cells. Why would you want to work on polymer solar cells? That's my question. And I'll tell you why not to work in polymer solar cells. But the idea again is to have a technology. And again, I must say this very carefully, because we have students to teach, right? So perhaps by doing polymer solar cells, you can teach people about polymers, you can teach people about solar cells, you can teach people about modules and so on and so forth. So as far as teaching is concerned, yes, there is some room for that. But that's not the whole room. It should not take all the space for learning this basic sciences. So I'll come back to that and talk about that a little bit more. So I thought that I would put this in. So as we talk about energy, as people in Pakistan talk about energy, we should keep in mind what is going on in the world and what are the things that is relevant, first of all, to Pakistan, number two, to the science in general, right? If they don't qualify either of those two, then we should be doing something else. So let's look at this. So this is the plot that everybody has seen many, many times. Anybody who gives any talk on solar cells have to show this plot. So these are plots of efficiencies of different types of solar cells, right? So we want. So as you know, the big guy in this scheme of things is the blue line, the silicon solar cells. They still occupy almost 90% of the market, and they are not going anywhere in any near future. But what is interesting is to see here what is happening here. This is where the polymer solar cells are, right? So nobody's working on it right now. As you can see that there are no more data points after a certain time, because they have all kinds of issues. I worked with polymer cells, and I my purpose was to look at the transport in those polymer solar cells. So maybe there is some room for some basic physics, yes. But if we are thinking about some application of that in Pakistan, those are not the things that we need to even think about. CZT, right? Inorganic solar cells. That's the diamond here, right there. These diamonds. CZT, almost history now. Nobody talks about CZT. You might see a paper here or there in the conferences, but nothing more than that. So that's also history. The only thing, so you can check all of these things, and see what technologies are still surviving, what technologies are not surviving. The two things that are obviously here to stay, one is this quantum dot solar cells right here, the white diamond, and the other one is this yellow dot, which are the perovskite solar cells. Okay, and quantum dot solar cells are now so easy to prepare. I mean, I cannot imagine that it would take either cost or the knowledge, immense cost or immense knowledge to produce those, to make those solar cells and to characterize them. So that certainly is possible, but there are some issues there, maybe net cost issues. But perovskite solar cells, That's something that is a lot of people are interested in. It is showing some promises, but the story is not closed there yet. These are all the people who are working on solar cells, perovskite-based solar cells. Some, for example, Saule technology. These are from Poland, right? They're doing work on flexible substrates, plastics. They are out in the testing mode right now, external testing, outside testing. So likewise, some of these Wonder Solars, they are from China. They have their modules out sitting in the open to look at the effect of the exposure to these solar cells. But look at these, right? Look at these numbers. These things, the best that we have are maybe 10 centimeter by 10 centimeter solar cell modules. Nothing bigger than that. As soon as you make these bigger, the uniformity goes to hell, and therefore the efficiency goes to hell. So how do you make a big module? My whole roof is covered with silicon solar cells that are guaranteed at 19% efficiency for 20 years. None of these come any close to those. They are cheap. They're dirt cheap. They're very easy to make. But there are issues that are related to, most importantly, their stability. Size is one of the big factor that you can see here. This is an article that recently came out in Nature. Size is a very big issue. As soon as you go to bigger size, all of these cases, the efficiency start to come down. But most importantly is this: it's a very unstable structure. There are just stability related to the way the perovskite cell is, as a function of temperature, particularly. Some of these, particularly this A, for example, or B especially, start to migrate. As soon as it starts to migrate, the structure goes away and you don't have the efficiency. It comes down from the best 17% to maybe as low as 3 to 4%. And it happens very fast in a high temperature situation. High temperature means, a rooftop in Pakistan, for example. So that, and then the good old issue of stability in moisture and all of that, that can be handled, because even today's silicon solar cells are also encapsulated in glass or something. That can be handled, but the stability of the structure cannot, we still don't have any solution for that. So even when we think about a technology like perovskite technology that is so prevalent, the research in the world, we still have to think about, there are companies who had invested a lot in perovskite are coming out of that because they don't see any way to compete with silicon, right? So maybe there's something else in terms of energy. Maybe solar energy is not the way to go as far as forward-looking research is concerned. I'm not sure about that. I'm not saying that is the case. But there are other options, for example, related to wind, related to other biospecies that one probably, if you contextualize Pakistan, maybe some effort in that area would be better time spent. So I think I'm just about out of time. I want to just conclude that there are still nanotechnologies that can be developed in Pakistan to address the issues of disease, food, energy, and water. We just have to be a little careful and little smart in selection of our technologies. There are some basic nanotechnology, and I'm not saying anything about giving up everything that is basic and apply all the effort in the application of the nanotechnology. Not so. We can still continue to do that, but there should be some balance between basic and applied nanotechnology. There has to be some intervention of industry to become a part of the solution, rather what they are right now, part of the problem, to have any economic path into future technology. And certainly government organizations, government labs, they have, everything that you can imagine. And there's one way of thinking there of how the technology should be utilized. Perhaps now it's time that we open it up and let it be available to everybody who can work in some of these important national security areas like disease, food, energy, and water. With that, I thank you very much. Thank you for the opportunity. It's I'm just thinking of a share by Nasir. मैं हूँ रात का 1 बजा है सूना रास्ता देख रहा है. तो इस वक्त यहाँ पे रात का 1:30 हुए हैं. I'll be happy to answer any questions, of course.
Thanks a lot, sir, for very informative talk. And it's pleasure, honor for us that you have joined us. Sir, that's right. Dr. Salma Wasim has put forward your name and she has done all the coordination with you
I know.
to getting
Wonderful.
all the your profile and talk and something like that.
Yes.
Now, participant, any question if you would like to ask from Professor Dr. Ismail Shah?
Assalamu alaikum, sir.
Walaikum salam, Safiya. Kya haal hai?
How are you, sir? Sir, kaise hain aap?
I'm good, but let's talk about the talk.
Sir, thank you very much for your very interesting talk. We are very happy to see you here after a very long time.
I'm happy to be here.
Thank you, sir. Thank you.
Hello, Dr. Shah.
Hello, Salma. How are you?
I'm fine. Your talk was very interesting and informative.
Thank you.
Thank
very
you
much.
for giving us time, sir.
You ask me, I will never say no.
Sir, वो भी आपकी रात का time.
It's okay.
अस्सलाम वालेकुम सर, मैं अरशद बोल रहा हूँ.
अरशद भट्टी. हाँ जी, अरशद.
क्या हाल है सर?
अल्लाह करम है.
मैं आपको बताऊं, इट्स वेरी हार्ड. अब नेक्स्ट टॉक मैंने देनी है, लेकिन यू हैव रेज्ड अ वेरी वेरी पर्टिनेंट इशू फॉर अस एक्चुअली. आई थिंक मैनी ऑफ अस विल गेट दैट. हाउ टू रिलेट द साइंस वी आर डूइंग टू द प्रॉब्लम्स अराउंड अस. ये एक एटीट्यूड इशू है जो हमारा वी आर फेसिंग, यू नो, transition. Now, you gave a wonderful example of this device you are working in Turkey, जिसमें photovoltaic, thermoelectric और photocatalysis को combine कर रहे हैं. So what you're doing is you're eliminating the need of battery or the electricity from the main power station.
Exactly.
We know all these three processes, लेकिन इसको combine कैसे करना? Then it comes some kind of engineering into that one. जो मेरा ख्याल में ना, जो मैंने पिछले 4-5 साल में ऑब्जर्व किया, एंड एक्चुअली आई एम ट्राइंग टू वर्क विद माय स्टूडेंट्स, इज टू ऐड सम इंजीनियरिंग एजुकेशन इनटू साइंस. कि आप छोटे छोटे जो कॉन्सेप्ट्स पढ़ते हैं उससे आप डिवाइसेस कैसे बना सकते हैं, मॉड्यूल्स कैसे बना सकते हैं. आई थिंक वी आर वेरी गुड एज साइंटिस्ट, बट वी लैक दिस इंजीनियरिंग कैपेबिलिटी. जो थोड़ी सी एफर्ट के साथ अपने स्टूडेंट्स में ऐड कर देना, I think then we are able to address these issues. Food security is another issue in Pakistan. और वो particularly इसलिए है कि we use a lot of pesticides and there is no control how much pesticide has to be used. And these days these nano sensors based on nanoparticles are being used. ये बिल्कुल वैसे ही जैसे वेस्टर्न एयरपोर्ट पे वो आपसे स्वाइप करते हैं ना, एक स्वैप करते हैं और फिर मशीन में डालते हैं. They look at the most probably Raman spectra of that one. So we are trying to work on something to develop the same for pesticides. ये जो हमसे. फिर दूसरा आपने वो you started this project, आपने नाम भी लिया for ये electrospinning instrument बनवाया आपने. And I'm happy to tell now we have 2 electrospinning instruments. एक डॉक्टर अनीस की लैब में और एक डॉक्टर सिद्वत की लैब में भी है, जो locally made electrospinning instruments हैं. It's very easy to make, and we know people who can do that. The only thing is you have to give them the design to do this thing. So I think this is wonderful to excite younger scientists कि आप थोड़ा सा इसको engineering के साथ सोचें ताकि आप problem को address कर सकें.
बिल्कुल सही. बिल्कुल सही. Arshad Bhatti is talking like a dean now. But I 100%
Dean
agree.
is going to retire soon.
Dean never retire. look at NM Bhatt Saab. He's still active and
He is, mashallah. He is.
mashallah.
Sir, at this I should mention here that I'm also thankful Dr. N.M. Bhatt. He was along with us yesterday, whole the day, and today he has also joined our webinar. So nice of you, sir.
Yes. He's a very nice man, and I'm very thankful to him for many things that he does to Pakistan science,
Yes.
and Pakistan people.
Yes, of course, and still doing.
And still doing. Yes, absolutely. एनएम भट्ट साहब आपका माइक स्पीकर बंद हुआ है.
Okay, sorry. It's always a pleasure to listen to you from a different perspective, always new things, innovative. I like to make two short comments. One is a national one. Your map shown of Pakistan was without Kashmir. So
Yes, I know. This is from
unconsciously.
This is report from Pakistan.
No, it is from the Google. Actually,
Yes, that's second one.
but recently, I have been talking about it for years. A British came in the HEC some 10 years back. I pointed, but this is a national thing, which I feel very strongly. So I think people take unconsciously from the Google. But now, recently, I think a few weeks back, government of Pakistan has issued a map including this.
I'll replace that map now.
You see, usually I
Me too.
red line even if I take from the Google. Anyway, second is very important. You have mentioned about the utilization of to the industries. But unfortunately, about 10 years back, there was a project which Canada gave to me, IDRC, about $175,000. And that was to see the possibility of utilization of nanotechnology in industry of Pakistan. So we proposed very quickly, I just mentioned this lot about it. We proposed two industries which were, from Pakistan point of view, dollar earning industries. That means textiles and sports goods. So I went myself twice to Sialkot to address to the Chamber of Commerce. There were about 60, 70 people, very, very rich people and so on. And they were interested, but they are buying these carbon nanotubes, some powder from putting into hockeys and selling it. So as Arshad Saab has mentioned about the mental thinking of the industries here, unfortunately, there is both ways. It's a debate which is being discussed for over 25 years, why industry doesn't come in to this. But in Pakistan Atomic Energy Commission, we had, because this was a different thing, 3 stages of lab to pilot scale to the industry. And when you come to labs, there's good, students can do it, professors can do it. When it comes to the pilot scale, is again somebody has to invest, and then to the industrial scale. And they are very difficult things to get the industry into. Anyway, we can discuss it as a very important part, but these are the difficulties for Pakistan to get the people into the industries. The research is there. So I think these are two comments which I wanted to make just for. Thank you, Ismail. Very nice.
Thank you, sir. If there is no question, I thank you, Dr. Ismat Shah, for joining us at such an odd time in your place. And we will look forward to see you in other activities as well, inshallah, soon. We will continue this series and we will want to see all you together here.
Matt, let me say one thing. आपने शुक्रिया अदा कर दिया, लेकिन I tell you, whatever nano boom you are seeing in Pakistan, we should all be thankful to two people particularly, Professor Ismat Shah and Professor Talat Rahman. They are the ones who actually came in late 90s, 99 or 2000 years was that, and then they met Dr. Taur Rahman. They convinced people in Islamabad that this is the area where you should be working. And then they joined hands with the people like Dr. N.M. Bhatt. And they, I think for next 5, 6, 7 years, we had a wonderful Nathiagali summer colleges, not only Nathiagali summer colleges, but then there were many universities who organized big events. For example, I, with Professor Ismat Shah, organized 3 international events where he was able to bring as many as sometimes 8, sometimes 10 people from Europe or America. And then, when these were organized in different universities, then they had access to our students and our academic institutions, their standards, and that led to many students who went for masters and PhD degrees abroad. And I remember once Professor Ismat Shah was the leading in USA to have the largest contingent from Pakistan. Am I right? So
yes,
ये जो contribution है ना, जो indirect, in-kind contribution इस मुल्क को दी है, I think that is huge. Thank you, sir. And probably I'm sitting here because of that initiative as well.
Oh, I don't know about that. Thank you, though. Thank you very much for mentioning.
And I hope this will continue. I think now we need to change the direction and bring these pure science research into the applied side.
Absolutely. All right, good. Thank you, Arshad.
Thank you, sir, once again, and thank you, Professor Dr. Arshad Bhatti, that you have highlighted these things, because all of us should know these all things about our seniors, and we should follow all these. Thank you very much, sir, once again.
Thank you. I'll listen to Arshad for a little bit and then go to bed.
Yes, sir, sir, you can continue, sir. Now I would want to invite Professor Dr. Arshad Salim Bhatti. Professor Dr. Arshad Salim Bhatti has vast teaching and research experience. He is one of those scientists who has been awarded Tamgha Imtiaz by the government of Pakistan in the year 2011. He has also been awarded Award of Excellence and Dedication by the Ministry of Science and Technology in 2002. Currently, he is working as Dean Faculty of Sciences, ComSats Institute of Information and Technology, Islamabad. Today, he will talk about the Exciton Plasmon interaction in metal semiconductor composites nanostructures. Sir, welcome to webinar, and please share your talk with us.
Okay, thank you very much. Let me upload my presentation. It's always very hard to speak after guru like Professor Ismat Shah, who has been wonderful. Let me see why it is not coming up here. And okay, here.
Sir, you are also teacher of many of us, so we are also waiting for your talk.
Almost there. You see it now.
Yes,
you
sir.
see it now?
Yes, sir.
Okay, and you hear me as well?
Yes, sir.
Bismillahirrahmanirrahim. Thank you very much, Professor Zohra Kiani, for invitation to speak in this international conference, where I happen to meet now Professor Ismat Shah, Professor Noor Muhammad Bar, and many other colleagues. It's always very hard to speak after guru like Ismat Shah, who has actually given a wonderful all-round view of not actually all-round, but then mostly related to photovoltaics and its application, the use of nanomaterials and those applications. What I'm going to talk today is exciton plasmon interactions. This is one of the phenomena which are being employed in not only in photovoltaics, in energy harvesting, in photocatalysis, and in many other applications. I'm sorry, I'm more physicist than a material scientist, but we are trying to understand this phenomena, and then we are trying to develop devices, particularly sensors based on these ones. So here's the brief layout of my talk. I'll start with nanostructures and quantum confinement, excitons, plasmons, give their basic definitions. Then what happens when we have a composite of semiconductor and metallic nanoparticles? There's an energy transfer mechanism both ways, which can lead to quenching or amplification of luminescence. And then the work we are doing recently in our lab, and event finally giving summary. Okay, let me, yeah, okay. Now, to start with, this is for the first few slides are for students, so please do bear with me, my teachers, if it looks boring to you. On the left side, we have got materials classification, with respect to its resistivity. We can define materials in three categories: insulators, and then semiconductors and conductors. And you can look at on the top is given their resistivity. Insulators are very highly resistive materials, ranging their resistivity 10 raised power 8 to 10 raised power 18 ohm centimeter. And then we have a class in between, which is a semiconductor, where the resistivity drops and goes to from 10 raised power 8 to 10 raised power -2, -3 ohm centimeter. And then we have conductors. And conductors are mostly metals. Semiconductors are silicon, germanium, gallium arsenide, and we know all the glasses and diamond, sulfur, and are the insulators. On the right side, we have silicon given on the scale of this resistivity. And the beauty of silicon is we can change its resistivity or the conductivity, if we go inversely, by doing the doping, by putting impurity atoms into silicon. And initially, when silicon was discovered and found that its resistivity or conductivity can be modified by putting impurity into it, people thought it's a dirty material, but then it became the heart of all the electronic revolution. All the electronic devices are based on silicon. So you can see it's a whole range of resistivity which can be changed by doing the by putting the impurity atoms into silicon. We cannot do much with the metals. Their conductivity remain the constant, but semiconductors are wonderful materials to play with if we want to change or tailor their transport properties by putting impurity atoms. Now, what are semiconductors? And now we talk about that in terms of energy band gaps of these three materials. Insulators have energy band gaps which are much larger, more than 5 electron volts, and it's very hard for thermally excited electrons to go from valence band to the conduction band. But as we go to the as we go to the conductors, we find that the valence band and conduction band overlap. And then what this dashed line is the Fermi energy, and we have a partially filled conduction band, and which helps the conductivity of the material. In case of semiconductor, the gap between the valence band and semiconductor is small. So it's a range of less than an electron volt to a few electron volts, and it can be crossed by an electron if we have some external energy source like some photon or some electron, or some, even if in the case of heat, we can have thermally excited electrons which can change its conductivity. On the right side, we have taken a table from the periodic table. You can see the elemental semiconductors are carbon, silicon. So we have graphite, actually graphene, silicon, germanium in group 4. And then if we go move away from group 4, then we have to have compound semiconductors. So group 3 and group 5, they combine, they make semiconductor like gallium arsenide or indium arsenide. And then we can have a group 2 and group 6 semiconductors like zinc sulfide, zinc oxide, oxide semiconductors in there. So we can make these semiconductor materials, and the band gap changes as well as we move away from the group 4. And we can play with this band gap, and we can play with the doping levels to change the both optical properties and the transport properties of semiconductors. Now, what happens is we reduce the dimensions. I'm sorry if you have seen this many times before, either today or yesterday or earlier than that. Very important is to know what happens if we reduce the dimension. To the density of states. So the physicists or physical chemists, they know more about that. We have a bulk material, which means the dimensions is much greater than the deep Broglie wavelength of the electron. What we see is the parabolic bands of valence band and the conduction band, the density of states, they change like that. But if we cut that one into a two-dimensional material, which means that the electrons or the carriers have degree of freedom only in a plane, then we convert this parabolic into step-like functions, and we can find only solutions where these steps exist, and then it changes in a stepwise. But if we reduce this plane into a single wire, so like a pencil, like a rod-like structure, so the carriers can move in one direction only, then we further modify these density of states, and they behave like quasi-atomic like behaviors with asymptotic behavior energy states. Now, the difference between the energy states in the one-dimensional or the two-dimensional materials does depend on the dimension of this physical dimension of the nanostructure. Now, if I cut this wire into a cube, which is very small, I make a quasi-atom. It's not a single atom. It's composed of many hundreds of many thousands of atoms, but it can behave like an atom. I convert these density of states into a discrete energy density of states. So the carriers can only exist at certain energies. The beauty of this one is if I change the dimension of this cube, I can change the energy position, and I can change the difference between the two energy states. That's the beauty of playing with the materials, playing with the dimensions of the materials, and that's very handy. So what we can do is we can define any device, and we can define its transport properties and its optical properties. For example, if we want to design a solar cell or photocatalysis, which should be active in visible, or which should be active in ultraviolet region, I can design these nanostructures to absorb energy in that region. Now, what happens is when we have a nanostructures, the quantum confinement effect comes into the play. Here's on the left side, we have the right side I've already explained. So on the left side, we have cadmium selenide nanocrystals. The size changes from 6 nanometers to 2 nanometers. And you can look at that 6 nanometers, the band gap is small. But as we decrease the size of the nanoparticles, now the color shows which wavelength it is going to absorb or emit when we shine light on it. So we go from red to the blue to the ultraviolet as we decrease the size. So if you do a simple Schrödinger wave equation solution of a quantum well, where the width of the quantum well, you just change the width of the quantum well, you will see that if you decrease the width of the quantum well, the energy states will be pushed up and the gap will increase over there. And that's the quantum confinement effect. And the width is defined by the diameter of this quantum dot, which is a spherical nanoparticle, cadmium selenide spherical nanoparticle. So we can design a whole range of these nanoparticles. You remember Professor Ismail Shah's talk, he actually spoke about TiA2 nanoparticles of, I think, 2 nanometers or 5 nanometers diameter, and then the surface area. So if you, what is important is the smaller the particles, the larger is the surface area as compared to its volume. And then that's very important for interacting with the outside world. If we have a large surface area. So that's very important. Number one, the surface area. Number two is what is the energy it is going to absorb. That's important as well. We want which part of the electromagnetic spectrum we want to absorb in our nanostructures, so that we can use it for some applications. Now coming to excitons. Excitons are fundamental excitations in semiconductors. We have a semiconductor where this is a valence band and we have a conduction band. A photon comes in, it excites an electron from the valence band and it goes into the conduction band. And if these, now we have an electron which is in the conduction band and a hole which is vacancy of an electron in the valence band. If they bind together using the Coulomb's force of attraction, then we call them exciton. This binding is for a very small time, and what happens is that if there's nothing, if there's no external field applied to take this electron away, this electron will recombine with that one within a few nanoseconds, or and annihilate this excitation, or this exciton will be lost. So we can create this exciton by shining light into semiconductors. We can have many types of excitons. I come to the next slide. Another important parameter is that this exciton, which I'm showing is here, is in a direct bandgap semiconductor, and it behaves like a hydrogen-like free exciton. So we have a plus charge here, and we have an electron which actually then moves around this this hole before it recombines with this one. And we have to have a certain radius of this exciton, which we call Bohr radius, which is around 30 nanometers for gallium arsenide. It is different for different materials because of the background dielectric constant of the material, which actually screens the electric field produced by these spheres. Now, if we look at now in the bottom one, over here, it is shown, which is figure C, and that electron is revolving around this hydrogen, which is a hole, and this is the radius of this orbit is known as Bohr radius. When we have an exciton form, what we see is a peak, strong exciton peak in the absorption spectrum over here. When there is no Coulomb interaction, we see a normal absorption edge. But once there is a Coulomb interaction, which binds this electron hole pair into an exciton, we see a peak over here. Sometimes this one is seen very strongly in the PL spectra as well at low temperature. Mind you, we can see only this at low temperature. At high temperature, we don't. At room temperature, we don't see this exciton because of a lot of phonons come into play. If we mask the phonon somehow, then we are able to see the exciton peak, and that we can only do if we do a low temperature absorption or low temperature photoluminescence. Now there are three different types of excitons depending on, we have free exciton, and then we go to the bound exciton, where free exciton is the one where electron and hole, they can move freely in their valence bond, valence and conduction bands respectively, but they remain bound to each other. But then we have other extreme where we get bound exciton, which means either one of the excitation, either hole or electron, is bound to a defect state or to impurity atom, and then the other one is revolving around it. And then there is a third type which is in between them. We call them charge transfer exciton, and they actually participate in transferring the energy from one material to another material through excitation. Now I come to surface plasmons quickly. We have metals, metal slab. So we just seen the excitons, and we know once exciton is formed, it behaves like a hydrogen atom. So it will have a field, its own field, which extends outside the space, which is roughly given by the Bohr radius as well. So if we have a nanostructure which is smaller than the Bohr radius, then this exciton radius will go outside the physical dimensions of the nanostructure. Now it can interact with the outside world. how it can interact. We come to this one before before looking at the interaction. Let's go through the surface plasmons. Now, surface plasmons are the charge density oscillations. It happens if we have a free electron gas, and the free electron gas, the simple example is a metal. So if we take any metal like copper, gold, or silver, it has got free carrier electrons, and we know that due to the Coulomb repulsion, all these electron gas come onto the surface. When they come onto the surface, and somehow if there is a photon which hits the surface, it creates oscillation in the charge density. So it depletes electrons from one region, and then these accumulate at the other one. So it kind of forms an oscillation, which we call charge density oscillations. And they do oscillation in a synchronized motion, and when the energy is quantized, we call them surface plasmon modes of the metal. You can look at that one over in this figure, where this oscillation is shown by plus plus minus signs, which show that density is of the electrons is increased and the density is decreased. So these density oscillations are seen, and how the field, because the density of the charge carriers is varied, then it produces a field which decays outside the surface of the metal exponentially, given over here, and it decays inside the metal. Outside the metal, it decays slowly as compared to inside. And again, it's the dielectric constant of the material where it is, which actually controls this leakage of the electric field. And now this is actually phenomena which is used in the biosensors using gold or metallic thin films, where this decaying field is used to interact with the bioenzymes, which changes the dielectric constant of the surface, and then any light which is reflected onto from the surface, its reflectivity curve changes, and then with the change of the reflectivity dip or the curve tells us what kind of material is on the top. On the right side bottom is the dispersion curve of the plasmons. We have this dashed line, horizontal line, which gives us the bulk plasmon frequency. The blue line is the light dispersion curve given by Cm omega is equal to Ck. And then this one over here is the curve, which is a red curve, which is the two-dimensional plasmon dispersion curve. And you can see that it never crosses the light and dispersion curve. It's always below the dispersion curve. Now that's one of the issue. We need to make these plasmons to interact with the light. So we need to have some kind of structures which can add some momentum to these plasmons. So, or we need to shift this one, the light dispersion curve, so that it can cut the plasmon dispersion curve to make it interact with that light. That can be done by using either a simple prism or the gratings. So we can add some momentum to the light, and so that it can cut and it can interact with the plasmons, or it can excite the plasmons. Now what happens is if we are in a low dimensional materials like nanoparticles, we already have seen this in the slab, but if we have nanoparticles, then these oscillations are strictly confined. The two phenomena which can happen depending on the wavelength of the light, either light can get scattered or light can get absorbed and excite the plasmon modes. Now these plasmons, when they excite, they produce inside nanoparticles, they produce very intense electric field around these nanoparticles. As we have seen that there's a decaying electric field. In the case of nanoparticles, this field is very strong and it extends to longer range. Now we can use this electric field to interact with the excitons. So we have quantum dots or nanomaterials, semiconductor nanomaterials, in the presence of plasmon field, which can shift their optical or transport properties. Now, once we have um, plasmons excited in a nanoparticles, there are three ways of decay of these plasmons. They cannot exist forever. There's always a decaying process of these plasmons, and they do, number one, by emitting a photon. So they decay by emitting a photon, or they can excite another electron. So they decay, the photon results into absorption, and then electron is injected to higher level. We call this hot electron, and that's very important. And this is what we want to do. Or they can produce a heat, so they can do local heating as well by producing phonons. So that's very important. So these three phenomena can happen. Most importantly, we need to have hot electron coming from these nanoparticles when we have excited plasmons. Okay, now we have excited plasmons over here. Now what happens is that, so left side I've already explained. I will go to the figure C on the right side, which I've taken from this paper. Now we have two materials. So one is a gain material, which is a semiconductor material, and on the right side we have a metal, which produces surface plasmons, and so there is a resonant energy transfer process. So if there is any energy state available which is in resonance with the surface plasmon energy, then we can have a stimulated emission in the gain medium. Now people are using this material, this phenomena, to produce plasmonic lasers. Not only the plasmonic lasers, but this is being used to transfer the information from one side of a conductor to the another side of a conductor with quantum dots attached on both sides using the plasmonics. So that's very important phenomena. We need to have resonance. Now what we can do is either we excite plasmons and then transfer energy from plasmons to the gain medium, or we excite in the gain medium using laser and then transfer energy to excite the plasmons. Both ways this can be done, and the two phenomena are given. The first one is the Forster resonance energy transfer mechanism. Example is given. We have two phosphor or chemophosphor molecules where we do excitation in one, and then we see the effect of this excitation as a fluorescence in the other molecule which are in the vicinity. So they are coupled with each other. They are coupled due to dipole coupling. Now what happens is that if we excite in the donor to the higher level, an electron from these are the LOMO levels and these are the HOMO levels, or these are, if this is a valence band, this is a conduction band, the excited electrons relax to the bottom, and then there are two ways. It can relax, it can come back to the valence band by emitting a fluorescence signal, or it can relax and go to the acceptor atom, and then it can lead to fluorescence from the acceptor atom. Or what happens is that it can come down and then it can excite from the fluorescence atom, and then it can from the acceptor atom, it can excite an excitation in the acceptor atom, and which can lead again to the fluorescence. So we can have excitation in the donor molecule, and we can see its effect as a increase in the fluorescence of the acceptor atom. The only way we can do is by exciting with a suitable energy over here. So that's an energy transfer mechanism. Now think we have one medium as a semiconductor and the other medium as a metal particle with surface plasmons. So we can see this effect over there. Okay, so this is one of the example of the FRET where very recently, few years ago, people have used the silver. silver nano- Is it possible कि आप mic बंद कर दें?
अपनी अपनी स्लाइड्स में मैंने ना डॉक्टर को मैंने लिखा है प्रोफेसर डॉक्टर
आप माइक ऑफ कर देंगी प्लीज?
मैं तो स्लाइड्स भी नहीं बनवाई मैं तो कह रही थी ना
हेलो
आप जो बनाएंगे सो वेरी मच होगा वही हुआ ना
ओके all right so we have a silver
Yes, sir, I'm doing. Girls, please be quiet.
उनको वैसे पता चल गया था कि हमारा 15 को ही होना था इस बार 14
हटे हटे ये इसको बस करना बस हो गया यही मसला है
okay so this is one of the example of FRET
Yes, sir, now
process.
please
We have a
continue.
silver
They are
nanowire and two quantum dots are attached on it. So one is excited and that excites the plasmon which travels and then this plasmon excites the quantum dot. So this plasmonics is being used for transfer of information using two quantum dots at the extreme end. Now here we have two processes. One is the plasmon induced resonance energy transfer and the other one is Foster resonance energy transfer. So we have a nanoparticle, we have a light shining onto it, and then it excites the surface plasmon. Two things it can happen. It can scatter back the light or emit the light, or it can excite an electron into what we call is a hot electron. If we have this nanoparticle embedded into a semiconductor. So if we take only pure semiconductor and shine a light onto it, it will excite and some of the light will pass through it without exciting some photons. But if we have nanoparticles in it, then most of the light will remain in the semiconductor. Some is absorbed by the semiconductor and some is being scattered by these nanoparticles or absorbed by the nanoparticles to excite the plasmons, and very small amount of this light will pass through it. So what happens is when this light is absorbed by the gold nanoparticles, it will produce hot electrons, and with these hot electrons can have energy higher than the barrier energy of the semiconductor. We form a Schottky junction over here. So this is a metal and this is a semiconductor. This is the conduction band of the semiconductor. So this electron, when goes to the higher level, it will go into the conduction band of the semiconductor. So it will go transfer its energy into the semiconductor. So once this happens, the process is known as PIRAT, which is plasmon-induced resonance energy transfer. And if we have the other way around, we have electron which is excited in the semiconductor, goes into the higher level, it goes into the metal and excites plasmon. If the process is reversed, then we have FRET process happening in this nanostructures. So the idea is to use these two phenomena to look into the zinc sulfide nanowires which we have grown and use gold over there and to see if we can quench certain photoluminescence in the semiconductors or not. The center one is an image which the bright spots show actually the plasmon field, and you can see and these ones are the TiO2 slabs which are on the right side, and you can see these bright spots going extended into the semiconductor material. Now we used vapor liquid solid mechanism to grow nanowires of zinc sulfide. It's a very simple technique. We have a metal film deposited on a silicon. In our case, we used manganese and tin. It's so thin that when we anneal it, they form blobs or small nanostructures, nano particles on the surface, and then we expose them to zinc sulfide vapor at high temperature, around 800, 700 degrees C. in a flowing zinc sulfide vapor pressure, vapors. They come onto the surface, vapors come onto the surface, they supersaturate the surface, and then they condense at the interface of this particle and the substrate, and they start growing into the wire-like structure, and we get a straight wire. This was demonstrated long ago by Professor Wu. They took the real-time TEM images to show the growth of silicon nanowires. But nevertheless, the phenomena is same for the all those which imply the vapor, liquid, solid, yeah, VLS technique. Now, why zinc sulfide? We use zinc sulfide. It has a band gap of around 3.7 electron volt. It's a wide band gap semiconductor material, highly luminescent, but it has got two intrinsic defects, which are zinc vacancies and sulfur vacancies. And when we have these vacancies, these are highly luminescent as well. For the case of sulfur vacancies, we get blue emission, something around 440 nanometers. And for the case of zinc vacancies, we get green emission, which is 520 nanometers. Usually, zinc sulfide is one of the oldest semiconductor material as well, is already used in the fluorescent materials to produce green light, because we have more zinc vacancies than the sulfur vacancies. But if we dope with some other impurity, like in our case, we have doped with manganese or with tin, we introduce impurity states, which gives us another band in the yellow or red part of the spectrum. So that's the important. Now these are particularly the green and the orange yellow, they fall in the resonance, plasmon resonance energy of the gold. This is just to show you, to demonstrate that if we dope with the different materials, with gold, tin, or manganese, if we dope zinc nanostructures, we get different colors as well. In the case of manganese, we get rainbow colors, the whole range of colors. In the case of tin, we also get mostly the green colors, but to a certain extent, we can get blue color as well. So that's very important. And if we change the size of the film we deposited for the VLS process, we can change this color combination as well. So this is the experiment we did. We had the zinc sulfide powder centered at the horizontal tube, took temperature to 1000 degrees. We have the substrate placed at certain distance, where the temperature was around in between the 700 to 800 degrees Celsius. We have nitrogen gas, which took these vapors to the substrate. Substrate already had metals coated onto that one, and then we grew the zinc sulfide nanostructures. Finally, we did the vacuum deposition of gold on these nanostructures. Just to give you how the band structure look like. On the left side, we have gold. So this is the Fermi energy of the gold, which is in thermal equilibrium with zinc sulfide. And we have the defect states given over here due to zinc vacancies, to the sulfur vacancies, interstitials, and due to manganese and tin defect states. This is the barrier height. We have around 1.25. We have conduction band over there in the case of zinc sulfide. So right side is zinc sulfide, left side is the gold. Just to give an idea, what happens is we do excitation. So the possibility is we have the transfer of carriers both way. If we have hot electrons from the plasmons, they will come to the zinc sulfide side. And if we have carriers in zinc sulfide excited, they can go to the plasmon to excite the plasmon modes. Basically, just to show you, this was a Schottky junction. So Schottky junction, remember, is only a one directional transport. It behaves like a diode. Now we did the temperature dependent. Now I'm coming to the last part of my presentation. We did the temperature dependent of zinc sulfide doped with manganese nanostructures. These two photoluminescence curves are taken from 10K to 300 Kelvin. with pure zinc sulfide. So there is no gold coating onto these ones. You can see, we see a very strong, at low temperature, 10K, a bluish line, and then we see a red line. We don't see much in the green over here. These are the transitions which we observe. We have schematically given over here. Now what happens is we put a gold on top of it. What we see is we complete elimination of this blue band and a strong emergent, even the intensity becomes much stronger of this red, yellowish red band. And we ascribe this process to the Pirate process, which is happening over here, given explained in this phenomena. We are still trying to work out the theoretical aspect of this one using simple laser equations, Einstein equations, how this energy transfer happens between the plasmons and the excitons of the zinc sulfide. Now these excitons are the bound excitons. These are not free excitons. Free excitons are seen somewhere around 320, 325 nanometers, which we don't see. We plotted the Arrhenius plots of these ones, and we see the intensity behavior is showing abnormal behavior. It's not normal. We see amplification of these modes as the temperature increases, which means the transfer of energy is seen. We fitted with these ones with the birth plot plots, and we determined the various activation energies and birth plot energy, which is not given over here from these nanostructures. And we are actually trying to quantify the role of plasmons in this transfer mechanism. Now we have another one set of experiments, zinc sulfide doped with tin, and now we did a coating of gold on these ones. Now this on the left side, top panel, zinc sulfide doped with tin PL, so without gold, is given over here, which shows a very bright, broad spectrum. So blue is very strong, and then we have a green and red, and it goes down. And this is actually a white light source, which we have predicted when we dope with certain amount of tin, because it controls the zinc and sulfur vacancies, and it creates on defects, which leads to this red and yellowish red defect states. Now what happens is when we what happened when we coated with the gold, we see that we at the low temperature all the bands which are which was very strong in pure zinc sulfide nanostructures doped with tin, they are suppressed, and the blue became very strong, and then it emerged, the green and the red emerged as the temperature rose. So this is again explained in terms of this Plasmon induced energy, resonant energy transfer mechanism, which is given on the right side. So how it plays its role, it's quite complex. We're still trying to understand it, and the only ways if we are able to do a proper theoretical modeling of this phenomena. Nevertheless, we have tried to explain schematically what is happening over here. So left side is the gold, and right side is this semiconductors, and we are seeing that we have got hard electron injection coming from plasmons into the zinc sulfide, and they only participate with certain defect states, not with all the defect states. That's very important. So if they fill all unoccupied defect states, then we get quenching of these defect states, because there is no hole for these electrons to recombine. So that's what we observed over here. We again did the analysis of by plotting the Arrhenius plots, looking at the abnormal behavior, looking at the range where this amplification is happening and where this quenching is happening. We are in the process of making an explanation to these ones. This is so far we have reached. in these experiments. So in the end, I would like to summarize that metal semiconductor nanostructures composites are interesting for multiple applications. Plasmon exciton interactions lead to transfer of energy from one medium to another medium. So I must say that this is one of the promising structures for energy harvesting as well, to be used in composite solar cells as well, or solar cells with capability of doing the photocatalysis as well. So applications are in energy harvesting, photocatalysis, plasmonics for information transfer. Plasmonic lasers are being people have demonstrated the laser using the plasmonics. We feel that the wide band gap semiconductors offer excellent opportunity because of the intrinsic defect states, which are highly luminescent. So highly luminescent means that their recombination from the defect states, the probability is high to emit a photon rather than a phonon. So that means, and they are in close resonance with the localized Plasmon modes of gold. And finally, we try to demonstrate that zinc sulfide doped doped with manganese and tin is being studied for bound exciton interactions with plasmons for amplification and quenching of luminescence using Pirate and Fret phenomena. So actually, we are interested in this work because we want to use this phenomena to produce a light source where we can tune different colors by tuning the plasmon excitation. If we have excitation, we can have more blue color or green color or red color coming out of the same source. So in the end, I would like to thank you for your patience, for listening me, Higher Education Commission for funding the two projects, for one for the vacuum chamber and the other one for Raman and photoluminescence. Then the work which I presented is the PhD work of Dr. Faiza Javed and Dr. Awais Ali, who is the assistant professor in our department. He's the one who actually handles the photoluminescence experiment, and all my students and colleagues in the lab. Thank you very much. If any question, I'm happy.
Thank you very much, sir, for your talk. And I'm seeing in the Zoom group chat, people are admiring your talk and they are just writing about it. So it's better if you ask questions, participants.
अस्सलाम वालेकुम सर, मैं डॉक्टर सबा बात कर रही हूँ. मैं maybe I am wrong, but you can clarify these things. You are observing most of these phenomena at low temperatures.
Yes.
So for practical applications, you have to do maybe on room temperature at least, or maybe at higher temperature. So can you please enhance on this point?
Okay, you're right. These phenomena are prominent at low temperature because we freeze phonons. But nevertheless, these phenomena are happening at the room temperature, but the noise level is quite high due to the phonons. So if we can make pure structures with less imperfections, then we can see these ones at the room temperature. What I feel is going to may happen is that its efficiency may not be the same as what its efficiency is at the low temperature. Nevertheless, it does happen over there. So eventually, we do low temperature because we want to understand the physics or the mechanism what is happening. But the practical device which will come out of it will for sure be working at the room temperature.
Thank you, sir.
Any other question or any comment?
Arshad, it's a very, very interesting talk. I've learned a lot. It's not my field, but as a student of Sure. A lot of Plasmon physics. Professor R.M. Chaudhary, way back in 50s, was talking about these plasmons when the high energy protons from the Cockcroft-Walton generator was striking the metals. But this explanation from based on the quantum physics was not there. So it's very interesting. I like to get one information on, can you have materials of with Bohr radius less than Bohr radius, or what are the materials?
Yes, you can have. Zinc oxide is an example where the Bohr radius is quite large. We can make a zinc oxide nanoparticles which has got its dimension less than its Bohr radius. What happens is that the Bohr radius or this electron's orbit does not remain this centrally symmetrical. It modifies according to its structure. So that is जो उसकी modification होती है ना वो उसके में PL spectrum में नजर आता है वो एक kind of a quantum stark effect नजर आता है उसमें. And that is because of this change in the orbit of the Bohr. ये जो Exciton का orbit है ना उसमें नजर आ जाता है. Yes, people have done it. People have done it. Gallium arsenide, aluminium gallium arsenide के quantum wells बनाए गए हैं. The dimensions was much smaller than the Bohr radius.
Sir, silicon is one example also. Silicon nanocrystals, they can also go below the Bohr radius.
अब तो बिल्कुल exactly right. तो अब you can make 1 nanometer, 2 nanometer. और तो वो जो उनसे Bohr radius is close to 10 nanometers, something like that.
The other very quick question is about the phonons at low temperatures. At room temperature, they are of the order of a few milli-electron volts. How do you confirm the phonons at low temperatures you mentioned?
So वो देखें Bose-Einstein अगर हम देखो ना distribution function. So the Bose-Einstein because these are the boson particles. तो इसकी जो population है ना वो जैसे temperature हम कम करते हैं ना तो its population goes down very rapidly. तो वो freeze हो जाते हैं. उसका ना amplitude जो है ना वो कम होना शुरू हो जाता है ना तो scattering amplitude उसका फिर बहुत कम हो जाता है. We cannot freeze them to zero, but the scattering amplitude really goes down. वो जो scattering cross section है ना it comes very small and they don't interact.
This is only a theoretical concept. No measurements have been made of the energies of these phonons, because at room temperature we were able to measure the energy of these phonons to a few millimeters using a few milli-electron volts using busbar spectroscopy. So at low temperature, obviously, it's only a theoretical aspect.
No, sir, you can do it with Rayleigh scattering.
I don't.
लाइट के साथ ना हम करते हैं इसको ना you are right. वो देखें सर वो जो you are absolutely right. You are expert in that. आपने ये जो न्यूट्रॉन स्कैटरिंग और ये सारा कुछ ये जो small momentum जो है ना the problem comes when we have to do the dispersion curve for the phonons.
Yeah.
तो उसमें फिर जितनी small energy के phonons है ना वो लाइट के साथ नहीं किए जा सकते.
Yeah.
So that's why we use particles in there. You're right in that.
Thank you. Thank you.
Okay. Thank you very much, sir, once again for taking time out from busy schedule and joining our webinar. It is really a pleasure and honor for us.
Thank you very much.
Yes, sir.
I had to cancel yesterday's, लेकिन वो मजबूरी हो गई थी करना पड़ गया था.
सर वो भी अल्लाह का शुक्र है मैनेज हो गया. डॉक्टर एनएम भट्ट के साथ एक्सचेंज हो गया.
नहीं वो मेरे उस्ताद हैं भट्ट साहब हम सब के he's mentor of the whole family of scientists. Actually, I wrote the other day. I was very pleasantly surprised, sir, that you are the students of Professor Rafi M. Chaudhary.
Mike, sir.
It was a history of, but that's some other time. A very
किसी वक्त आपने हमें बताना है उनके मुतालिक। I have the honor of meeting him, लेकिन ये नई जनरेशन को पता होना चाहिए कि पाकिस्तान के शुरू के साइंटिस्ट कैसे थे।
एक्चुअली ये नईम बुखारी ने 1981 में 1 आवर का प्रोग्राम किया था रफी चौधरी साहब के साथ। वो मेरे का प्रोग्राम है, आई कैन लर्न यू सम टाइम, बट देयर इज लॉट I've got about 120 over 100 letters from Professor R.M. Chaudhary because I was one of his let's say lovable students. And
I think he mentioned you many times.
Yeah, one hour before, I think 1 month before his death, I got a letter from him and so on. So we were in correspondence. It's a history, but it's a pleasure to talk. We'll talk sometime personally. Thank you very much.
Dr. Bhatti, I also want to share with you that his 3 daughters were teaching in physics department LCWU.
हाँ जी, बिल्कुल।
जी।
मैं उनके दोनों बेटों से मिला हुआ हूँ, one in Cambridge and one Dr. Anwar Chaudhary, who is in Australia, I think. चलें।
Okay, sir. Okay. Thank you very much, sir. Thank you for joining us.
Thank you very much. Thanks a lot.
Now I want to invite the next speaker, Dr. Muhammad Saifullah Awan. Dr. Muhammad Saifullah Awan is a principal scientific officer at National Center for Physics. His research focuses on magnetism and magnetic material, microwave nanocomposite, both bulk and thin films, and shape memory alloys. He has published more than 95 international research papers in impact factor journals. He is the recipient of Research Productivity Award in year 2013, and also he has got awards on Best Oral Presentation in 2009 and 2011. Today, he's sharing his work with us about magnetic hardening in metallic magnets at nanoscale. Dr. Sab, we welcome you in our webinar, and we are looking forward to listen to your talk.
Thank you very much. Can you hear me, please?
Yes. Your sound is coming.
My screen is clear.
No, you are not looking. We can't see you.
No, please, you can see my screen.
Yes. Your screen is visible.
Okay, right. Thank you. Thank you very much, Dr. Zohra Kani, for inviting me in the galaxy of scientists like Arshad Salim Bhatti, Ismat Shah, and N.M. Bhatt Sahab. These people are always inspiring for us. Dr. Arshad Salim Bhatti was asking that, telling that it is very hard to speak before the gurus like Ismat Shah, and I have 2 gurus because Dr. Arshad Salim Bhatti is my PhD supervisor and Ismat Shah is my PhD thesis evaluator. Assalamu alaikum, sir. Okay, I think he has left the chat. Anyway, today we will talk about magnetic hardening in metallic magnets at nanoscale. This is the overview of my talk. I will give you the motivation behind my work and then some introduction about the magnets, selection criteria, and then typical for the magnets. I am going to discuss its phase diagram and a very typical and magical heat treatment cycle. Then, of course, experimental procedure, characterization, and results will be discussed. And finally, I will conclude my talk. Of course, applications of these magnets. I would like to start from the last one just to create interest in the presentation. Magnetis, how it is used in our daily life. Almost around every one of us is with magnet. At least we have cell phone in our pockets. So here are a few very interesting applications of the magnets. Like these magnets are used in hard drives. Like here in hard drives, this is the ND magnet. These magnets are used in high-tech helium leak detectors. These are the mixed ferrite helium leak detectors in which helium ions flow and deflect. Then tons of magnets are used in wind tunnels like NDFEB, and tons of magnets are used in MRI machine, and then a lot of magnets are used in our car. Then these magnets are also used in oil filtering. They are used in loudspeakers, DC motors, magnetic separators like physiotherapy. They are used as magnetotherapy, and then they are used in purse of ladies and in toys of the boys. So around us, there are a lot of applications, these magnetic materials. Okay. The main motivation behind this work was to develop the anisotropic magnetic alloy with optimum magnetic properties. Here in the cloud, I had a question that in the periodic table, there are a lot of elements. Every element of the periodic table can take part for a permanent magnet. Actually, it is the question. Is it possible that we took any one of the element and can make a permanent magnet or soft magnet? Of course, the answer is no. We can't put any element to prepare any kind of magnet. Then there must be some criteria for the selection of materials from the periodic table for the magnet. What are these criteria? Number one, the material must have high magnetic moment. Second, it should have high Curie temperature. Number three, if there are more than one element, then they should couple ferromagnetically and ferrimagnetically rather than antiferromagnetically. And last but not the least, most important is the magnetocrystalline anisotropy to develop the directional property in the magnets. Here in the periodic table, we looked at the elements of the transition metal, and lanthanides are the potential candidates for the magnetic materials. Like most of us know that samarium from the lanthanide and cobalt from the 3D elements are the potential candidates which form the samarium cobalt magnets, which are the hardest magnets nowadays. Then neodymium from the lanthanide and iron and boron from the transition, they are also very much potential candidate for the hard magnets. Then a family from the 3D transition elements, iron, chromium, cobalt, they also form a good family of magnets. But today we will talk about the iron-based magnets, which includes iron, cobalt, nickel, and aluminum, and minor quantities of niobium, titanium, copper, and sulfur for the fabrication of magnetic materials. Magnetic hardening. Most of you may know these hysteresis loop that whenever we say magnetic hardening means that how much the magnetic is hard. Whenever I said hard, it doesn't mean it is mechanically hard. Rather, it is magnetically hard. So it is very difficult to magnetize these materials and very difficult to demagnetize these materials. So here across the edges, we have the porosity for these magnets. The wider this gap, the harder will be the magnet. So there must be some mechanism behind this hardening of this material. If we have a ferromagnetic phase, then we must have some non-ferromagnetic or least ferromagnetic phase, so that the two ferromagnetic phases must be separated by a non-ferromagnetic phases. If such structure is developed in the magnets, then we can get the maximum corrosivity and good magnetic properties of these alloys. Actually, this is one of the phenomena. Other families of the magnets have some other different phenomena. But in this case, we will try to develop ferromagnetic phases and least ferromagnetic or non-ferromagnetic phases alternatively, and these will contribute towards the hardening of this material. And finally, this material can be used as permanent magnet as we desire. So this was the composition of the alloy which we have prepared by vacuum induction melting. Iron was the balance, rest composition is written here. The composition was determined by ICP technique. These are the rods which were developed by vacuum induction melting. So this is the phase diagram of our system. In the left side we have iron and cobalt, and in the right side we have nickel and copper, which also include aluminum and titanium and sulfur. Here we have the composition which we have prepared. When we mix all these materials and melt almost above 1400 degrees Celsius, the material is in the liquidous form. So when this material is cooled down, it undergoes different phase transformation, like from liquid to alpha phase, pure alpha phase, from alpha to gamma phase, and then alpha plus gamma phase, and then alpha prime phase. So when we cool this material to room temperature, if we cool slowly, then we may come across various phases in the alloy. And some of these phases are very harmful, like gamma phase. So in order to avoid this, once we cast this alloy, then this material is heated up to the single phase alpha, and then it is quenched. Either it is air quenched or oil quenched. So during quenching this material, we can avoid the undesired phases like gamma phases. But when we quench this material, it will come across this region. This narrow region is very important. It is very close to the Curie temperature of the material. Actually, when we quench this material from a single phase, which is alpha 1, definitely below the liquidous phase, in this region, the material splits into two phases. We will call them alpha 1 phase and alpha 2 phase. Normally, alpha 1 phase is iron and cobalt rich, and alpha 2 phase is nickel and copper rich. It means this is more ferromagnetic and this is less ferromagnetic. But in in iron and cobalt phase, there may be present nickel and copper. And on the other hand, in nickel copper rich phase, we may have iron and cobalt. But our expertise is this, that we have to make this alpha 1 phase almost pure iron cobalt phase, which may not include nickel and copper, and on the other hand, alpha 2 phase must be pure nickel and copper and other elements rich, but it may not include iron and cobalt, so that it is perfectly ferromagnetic phase, and this is perfectly non-ferromagnetic phase. But when we quench this material, and this material across this temperature, which is close to the Curie temperature of the alloy, it splits into two phases, alpha 1 phase and alpha 2 phase. This splitting is actually due to the miscibility gap between alpha 1 and alpha 2. Here you can see the animation that when we quench the alpha 1 phase, it will split into dark and white patches. These are actually alpha 1 and alpha 2 phases. So the composition gradient between these alpha 1 and alpha 2 phases, they are responsible for magnetic hardening and saturation or maximum magnetization of these materials. The higher the composition gradient between the alpha 1 and alpha 2, or finer the grains of alpha 1 and alpha 2, the higher will be the properties of the material, which includes porosity, remanence, and maximum magnetization. Okay, this is the typical magical heat treatment cycle, complicated and time-taking, which will develop the corrosivity and other properties in the magnet. It includes basically 4 steps. In the first step, the cast material is homogenized at some temperature which is below the liquidous temperature and also below the gamma phase temperature. It is almost 1200 or 1250 degrees Celsius. And then material is quenched, and then again it is heated up to the just below the Curie temperature. But in the influence of magnetic field. Yani ki at the same time, when we heat this material below Curie temperature, magnetic field is applied so that the two phases which are magnetic and non-magnetic, they are under the influence of this magnetic field. So under this magnetic field, when material is heated, the magnetic phase, which is alpha 1 phase, which is iron cobalt rich phase, will respond and elongate towards the along the magnetic field. And after a certain period of time, they, when it attain a maximum length along the field, it may break and this process continues. For a certain period of time, we apply the magnetic field, like in our case, we apply the magnetic field at 800 degrees Celsius for only 10 minutes. Although we have tried a lot of others, but I am quoting here for 10 minutes. Then material is again cooled. After that, we give two heat treatment cycles, which are called step aging. First step was solution treatment. Second step is TMT. TMT stands for thermomagnetic treatment. And the third and fourth steps, these are actually step aging. We heat treat this material under argon atmosphere at 640 degrees Celsius for 3 to 4 hours. And then again, this material is heated at 550 degrees Celsius almost for 24 hours. These temperatures can be tailored or changed according to your composition. So in the TMT region, thermomagnetic treatment region, actually alpha 1 phase will respond and its volume fraction will increase and porosity is developed. And in the step aging treatments, actually solid state diffusion will take place, and the iron and cobalt which was present in the alpha 2 phase will migrate towards the alpha phase, alpha 1 phase, and copper and nickel which was present in the alpha 1 phase will migrate towards the alpha 2 phase. So this migration will create a composition gradient between alpha 1 and alpha 2, making alpha 1 a good ferromagnetic and making alpha 2 as least ferromagnetic or non-ferromagnetic. So if this situation is achieved, then we have very good corrosivity of the magnets, and of course good magnetization could be achieved. So these three steps, which are solution treatment, thermomagnetic treatment, and step aging, we have some prerequisites. Like for the solution treatment, the material should be in the single phase, that it must be in the alpha phase, and then it should be quenched. Next, TMT, thermomagnetic treatment. For thermomagnetic treatment, material should be lie somewhat here in the two-phase structure. Material should be in the two-phase region. Temperature should be less than Curie temperature. It is important. Temperature should provide required diffusion rate in the magnetic field, and this temperature should never enter in the gamma phase, as gamma phase is not good for the magnetic properties. Third step is the step aging. Step aging temperature, for step aging temperature should have high enough short range atomic diffusion. Aging time must be sufficient high for diffusion. That is why at these temperature they are heat treated almost for 24 to 48 hours. And temperature should never enter the region of gamma phase region stability. That is why this is harmful for the magnetic materials. So if all these prerequisites are managed, then we can get good magnetic properties. This is the arrangement which was used for thermomagnetic treatment. This is actually a self-made electromagnet, 1.5 Tesla electromagnet. Here we place the magnet. These are the poles, and on these poles here we put the magnet. So magnetic field will start from here, enter here, and pass on. And for heat treatment, we made a heater, which we put this heater on this U-shaped magnet, and temperature of 800 or 850 degrees Celsius is achieved, and for certain period of time, 5 minutes, 10 minutes, or 15 minutes, this magnet is heated at that temperature, which is below the Curie temperature, These are the optical micrographs of the magnets. Here we can see the cast structure alloy, which is equiaxial in grains. And for high magnification, you can see within the grains, we have titanium-rich precipitates. Actually, these titanium-rich precipitates are responsible for the removal of inclusions in the material. For higher magnification, these are the field emission scanning electron micrographs taken along the field when field was applied and perpendicular to the field. If this is the magnet, you can see field was applied in this direction from bottom to up. So you can see that when field is applied along the length direction and material is observed from the top, you can see fine rods. This material was actually etched in the acidic solution. And for this inside shows the higher magnified view. Here you can see the rod length. It varies, but depends upon from almost from 0.5 micron or something like 0.1 or 0.2. But when we look this material from the top, it looks like dots. So these dots, these are shown the higher magnification view. Here you can see the micron marker is 0.1 micron. So the one dot is almost less than 100, I think 50 to 60 nanometer. And this is alpha 1 phase. The bright portions are alpha 1 phase, and the region between bright portion is the alpha 2 phase. So alpha 1 phase, which is magnetic and iron and cobalt rich, is separated by the non-magnetic phase. So we have countless alpha 1 and alpha 2 regions in our material, and these materials actually phases actually define the corrosivity and the other magnetic properties of the alloys. So
Excuse me,
finally, these are the only 2 minutes.
Interrupting you. Okay, please, then conclude, please.
Okay, this is the last slide. Okay, these are the final magnetic properties of the alloy. Here you can see homogenization, thermomagnetic treatment, first aging, second aging, and at magnetic properties. So at the end of the day, finally, we have achieved a magnet with the corrosivity of 1.5 K, with the corrosivity 1.5 K, and with readiness 10 K, and the energy product of 5.3 megagauss constant. So these are the actually optimum magnetic properties for this composition for this alloy. This is the hysteresis loop after the final heat treatment cycle. Here we can see a very good squareness in the loop, which is actually the requirement for the good magnetic material. So finally, I will conclude my talk. We have developed the anisotropic alloy, and vacuum induction melting produces equivalent thermomagnetic treatment. We produce alpha 1 phase, and SEM revealed the 2-phase structure, alpha 1 and alpha 2. Thank you very much. Any questions, please? Welcome.
Thank you,
Excuse me, Dr. Saif.
Yes.
Can you hear me?
Yes, I can hear.
Yes. Can you please shed some light regarding the impact of magnetic field on the permeability of a material particle? If the magnetic field is very, very high, as I think it will be very important for the BH curves.
Yes, actually it is the inherent property of your magnetic material. Either it is permeable or not. Of course, when we align the material in some particular direction, we have maximum properties in that direction and least properties at the 90 angle. So permeability of the material actually depends upon the material composition and definitely its heat treatment cycle. These properties can vary.
Yes, you are very, very right. But I think so in the presence of the magnetic field, in the presence of the super strong magnetic field, the permeability, instead of being a function of the composition, it will be a function of magnetic field intensity, I think so.
Yes, of course. And it also depends upon the time factor also.
No, when the magnetic field will be very high, then I think so it will be dominating all other physical parameters.
You can, yes, you are right.
Dr. Zina, sorry for interrupting you. Actually, other speakers are waiting.
Okay, all right.
We will discuss later on with Dr. Saif.
Okay, all right.
Okay, thanks a
Most
lot.
welcome.
Thanks for understanding. Thanks, Dr. Saif, for joining our webinar.
Thank you.
Now, according to our schedule, the next talk was of Dr. Naveed Zafar. Sir, are you with us?
Professor Zora, I'm with you.
If you don't mind, just I want to request you that one of foreign speaker is waiting for a long time. If we can take him on board first, if you don't mind, please.
Doesn't matter, yeah. Please go on.
Thanks a lot. Then I will take you on board after Professor Dutta.
Okay.
Thank you very much, Dr. Zora. I'm so sorry, everyone, because I have another talk in a conference after this. Okay. It gives me immense pleasure to see you all. And thank you very much for this opportunity to introduce a completely new technology about desalination of water. So what I'll do is I will quickly go through some of the slides, but before even coming into it, I wanted to just cite a quote from Locke, and I let you read it because that's where we are today. We need new ideas and innovation together with entrepreneurial spirit to be able to succeed. And I hope you can do that also in Lahore. The reason behind is globalization has cut short any boundaries, and that has given rise to the fact that irrespective of where in the society we live, we have equal access to everything. And as a professor, that is the best thing that we can think of. Water is one of the most essential part of our life because we consist of 70% water, maybe not me, I'm old, so I will be maybe 60% water. And also, there is a severe shortage of it globally. And on top of that, we are also polluting it across the board. Most polluting part of it is when we extract water, and places where we are extracting water, extracting oil, have shortage of water. Further complication due to human abuse, we get water when we don't need it, and we don't get water when we need it. So global warming is leading to climate changes. That is leading to decline in food production. So it's a wake-up time for all of us to find new solutions. I'm going to introduce a technology that I started developing back in Thailand when I was at the Asian Institute of Technology, where I actually met Anika and appreciate the kind invitation today. So our goal is to try and figure out whether we can contribute to relieving the water stress in countries. And as you can see, this is not limited to any country. It is worldwide. Even in Sweden, there are pockets where we have severe problems with water. Let's go back to physics. If we have fresh water and we put two electrodes, we charge the electrodes positive and negative. Then the electrodes will take away the cations and the anions. This is typically how a capacitor would charge. Based on this technique, we developed what we call the capacitive deionization system. Of course, before us, there's been others as well doing it. The innovation that we did, I will try and introduce later. But first of all, let us look at the ion removal process. If you have positive and negatively charged electrodes, then you are able to remove the sodium and the chlorine. This is what we call electrosorption process. And higher is the surface area of the electrodes, higher is the ion adsorption. So effectively, one wants to have a supercapacitor.
दूध पियो भाई मैं गरम किया उधर से पंखा चलाओ क्या हलवा बाद में देती पहले दूध पियो.
May I request you to please mute your mic? Thank you.
Sir, we are doing this.
No problem. So once the electrodes are saturated, one can simply reverse the polarity and you can wash away the salt that was adsorbed, which is basically the brine solution that is thrown. The advantage with this is that since it's an electrical process, we end up getting the work done at very low power consumption. We also have advantages that scaling and fouling are reduced. Since we are using voltages less than 1.23 volt, because that's the water splitting conditions that you reach. So electrodes don't deteriorate, and we have absolutely no pressure drop or pressure required. We have some limitations. Only ions can be removed because this is not a filter. In reverse osmosis or any other water treatment technologies, you are taking out water from the mixture. In our case, we are taking out the salt from the water. We have a high salt rejection capacity in reverse osmosis, while in CDI, you can actually stop where you want. For example, in agriculture uses, one can survive with 1000 ppm salt. And for drinking water, one needs 250 to 300 ppm. In Sweden is 220 ppm ions. So effectively, you can stop where you want. You don't have to do extra work. And that's where, again, one saves energy. If we compare the different technologies that are available, then you can see the power requirements in each case. So capacitive deionization for brackish water, that's what we think is viable today, is quite low energy consumption. Okay, Let's take a look at some of the facts that is there. If we have an electrode, this is the electrode that we use. It's a carbon cloth, which we buy off the shelf. And then if you fix it onto a flat sheet, then we try to see what is the best way that we can have the maximum flow through our electrodes. And while optimizing it, we have been able to see that, if we have a circular system, probably that's not the best, but we can have an entry point at the middle and then it flows through. It's very nice for the lab use, but it's not practical because it has to be scaled up to be able to reach the people. However, what we can determine from here is that depending, this is a flow through system that we follow, and that's the uniqueness in our CDI system compared to others that are being, published by other groups. In the other side, they do flow direction is like this. So in that case, one is getting just the surface to absorb the salt ions. In our case, the water goes through the electrodes, and these electrodes are typically 1,000 square meter of surface area per gram. Like the activated carbon cloth I showed you is about 1,100 square meter per gram. One can play with other configurations as well. One can have a symmetric configuration like any electrolytic capacitor, or asymmetric configuration. I will like you to note the concentration that keeps concentration curve here. If you look at it, the concentration here means the ionic concentration in water, and with increasing voltage, we see that the ion concentration reduces more steeply. In other words, one can do multiple work within a period of time to increase the throughput. With asymmetric electrodes, with symmetric electrodes, that is feasible, that is possible. Without going into more details of the electrode engineering, which I will touch base later, let me try and give you an example of some brackish water desalination that we carried out in Oman. This was from Al-Lawami, and we had a concentration of about 2,000 ppm salt. So we could get a pretty uniform, removal of salt with a power consumption which was less than 1 kilowatt hour. Currently, what we are doing is we are solely focusing on modification of the electrode surface. One of these examples is here. By fluorination of the electrodes, we are able to increase the open circuit potential, and that leads to extremely nice desalination efficiency, as well as we do some work on water splitting for hydrogen production, and fluorination helps to reduce oxidation of the electrodes. So this is just an example. Again, I will request you to take a look at the steepness of this curve. As you can see that we are able to extract the ions much more quickly. So one can do multiple cycles within a given period of time. So what we notice is that fluorination, it actually increases the charge removal efficiency, and one can then, get much steeper, much faster removal of sodium chloride. Since it is a capacitor, we try to also increase the capacitance. This is just an example. We took some zinc oxide nanorods, plugged it onto the electrodes, and then we checked the desalination efficiency. Wherever the salt concentration goes down, that means this is desalination. And when the salt concentration goes up, this is regeneration. So you can see that you can improve the desalination by, putting dielectric coatings. This is the specific salt adsorption that we were getting, and we were getting around 8 milligram per gram. This is an old result. These days, we are classically getting about 12 to 15 milligram per gram in the lab. The electron modification, essentially, what it does, it, again, basic physics, it actually aligns the electric field from one electrode to the other, okay? And by using a rod, we are able to actually have a very high electric field at the tip, and that helps in the ion adsorption as well. So these are some more results. I will just skip it and give you the most optimized values that we were getting. It's about 13.5 milligram per gram that we are able to remove during with the zinc oxide nanorods. Of course, modeling goes hand in hand with the experiments. And we have been looking at, what we have termed as ASAR, or adsorption, specific salt adsorption ratio. And we were checking up how we stand. And it seems that, zinc oxide ACC is quite similar to the titania coatings, but it's much better than just having simple electrodes made of activated carbon. Currently, we are interested in the Faraday mode. Till now, I was talking about the capacitive mode, that is some place where you are not splitting the water. But as soon as we start going into the Faraday mode with voltages of 2-3 volts, then one starts degrading the electrode material. So what we did was we coated it with, coated these fibers with boron nitride. Boron nitride is known to have a very high dielectric constant. And we tested long-term stability of it. And it seems that you can increase the capacitance. And also, we are able to have long-term stability of these electrodes at higher voltages. From desalination, we are moving to the other side of the game, that is to reduce contaminants. And in this side, we are using it for removal of bacteria, for removal of PFAS, for removal of organic contaminants, etc. But in order to better understand all these processes, we developed a new model called a dynamic Langmuir model, by which we are able to essentially predict what is going to be the characteristics of a device dependent on 1 or 2 experiments. I'll give you example. Supposing in Lahore you find a well which has 3000 ppm salt. Another place you have 1000 ppm salt, and you want to use it in a place where you don't know what is the salt concentration. So how you are going to use the device for continuous use. So by doing a couple of experiments in the lab, we can predict how a device will perform for any concentration of salts. That's what we have developed over the last 5 years. Okay, these are all published papers, open access, and we have also given access to the computer codes. So please feel free to model it, and if you need any assistance from us, just get in touch. So we are able to essentially model CDI results from other people as well. It's possibly one of the first model that can take on multiple devices. Because till now, it has been that each group had their own model. So, of course, when you come up with a new theory, it's always difficult to publish. We struggled for first 2 years, but now it's okay. It's understood that our model is more or less the standard in CDI. Okay. So effectively, what I introduced to you all is two highly porous surfaces through which we pass the ions using a small voltage to separate these ions. The major discovery in our lab has been to try and see what happens if we plug in a third electrode. Okay, and that's not very unknown. You know, this is from Bangkok, this is from Greece, and this was from India, where you have a third electrode to try and see everywhere. So by putting in a third electrode, which we initially called a triode, we were able to basically modify the electric field inside a device, and that leads to a higher charge efficiency and a lower power consumption. So this has led to the birth of a new company here in Stockholm, which is called Stockholm Water Technology, wherein we are essentially talking about these three electrode systems. I'll give you some more examples wherein we have used real life water, and we have done disinfection of water because fortunately all bacteria and microbes are also charged. So anything that is charged, you can discharge with CDI. I will go away from this. In order to come to this, we had to work pretty hard, as I said, from 2006 onwards. And these are some of these phases of development into what we have launched last year as a product in a company. I am no longer involved much with the company, but it's one of my old students who has taken over. It's a reasonable sized company now, trying to produce and making non-membrane based water deionization systems. So I want to end today with a small video, and I will request you to look. with this, I think I will quickly let you see what we are working on. This CDI is one of the things, but we have a lot of other work that is going on in the group. And I think, Dr. Zohra, thank you very much. I hope I have introduced the energy-water nexus, which Anika wanted me to introduce.
Yes, sir. Thank you very much, sir, for joining us and giving time for our webinar. A very informative and diverse talk. We have gained a lot of knowledge from this your talk. If any question participant want to ask any one or two quick question, please.
That is very interesting. Desalination is an old problem of 1960s. In Karachi, we planned for some desalination plant at the time, but it's a new venture, I think, more economical. Has it been, has the drinking water reduced economically?
Yes, it has been in Sweden. It has been already sold to a couple of companies, and one company is using it for making drinking water in the island of Gotland, and they have marketed more than 150,000 bottles of water. So this technology has been on since 2018, November.
Okay. It's a player. It takes me back some 50 years when I was at KTH for a few weeks.
Okay.
Drottning Christina's wig.
Wig. Oh my God. Okay, that's
there was a nuclear reactor underground, and I spent a few weeks experimentation on that research reactor. Very nice, very old memories of Stockholm. Thank you very much. Going back to very old days. A pleasure to listen. Thank you.
Yes, thank you very much. And at the end, I must introduce you just in few lines that Professor Datta is Chair of Functional Materials at KTH, Royal Institute of Technology, Stockholm, Sweden, since 2015. Professor Datta, it is important to tell just for our students to know that where you are working. And his research focus resolves around application of nanomaterial for energy and environmental mitigation. Professor Datta is an award-winning author of the book Fundamental of Nanotechnology. Professor Datta has more than 200 peer-reviewed research publications with more than 10,000 citations, that is H-index 50, 11 chapters in science and technology, references books, and 10 patents. Thanks very much, Professor Saab, for joining us and giving us an opportunity to listen to you.
Thank you. And Dr. Zohra, please come and visit us here in Sweden.
Inshallah, we will come and visit you. Thanks a lot.
Thank you. Bye-bye.
Our next speaker is Dr. Naveed Zafar. Dr. Naveed Zafar is a senior scientist in Experimental Physics Department, National Center for Physics, Quaid-e-Azam University Campus, Islamabad. His focus is on the study of interplay between the crystallography and magnetism in oxides. He has been awarded a number of national and international awards and has over hundreds of citations. Dr. Naveed Zafar has waited for some time. I really appreciate this activity, and I must tell here that he is telling us that exploring the dynamics of molecular rotors in novel framework materials for renewable energy technology. Thanks, Dr. Zafar, Naveed Zafar, for joining us, and please start your talk.
Thank you, Dr. Zohra, for your invitation. Can you listen me?
Yes.
Can you see my slides?
No, slides are not just shown, just we are getting your LCW talk is written. You have to go slide share, slide shows.
Okay, give me a second, please. Sorry.
Okay.
So I did already.
Yes. Now it's fine.
Okay, thanks a lot for your kind invitation and for giving me the opportunity to talk in front of learned audience. My talk will be focusing on exploring the dynamics of molecular rotor and novel framework material for renewable energy technology. You have already introduced me in front of audience, but I would like to focus what kind of research directions I am working on. Right now I have few students working on metal organic frameworks for hydrogen storage. My PhD experience and my essence of my research is structured property relation in novel metal oxides, focusing on phase transition and magnetism. Apart from that, I have few students working on ultra high temperature ceramic coatings and smart anti-corrosive composite coatings. Besides, I'm also working on new cathode material for lithium ion batteries. If any student is interested to work in these areas, they can contact me via email. Now, coming to the talk. Whenever you talk about the renewable energy technology, either the name of battery or fuel cell comes into mind. But there is a big difference between the two different domains. In battery technology, batteries generate power electrochemically, and luckily in fuel cell, they also generate power electrochemically, but there are slight differences. In batteries, there are electrodes as the working material, like lithium cobalt oxide and so on, alpha sodium ferrite family of structures. And in fuel cell, we have gases as the working material, like hydrogen and oxygen, and the product is water. So it's a very clean technology in the coming decade. Electrodes gets consumed with the passage of time in battery, whereas electrodes do not get consumed in fuel cell. They have a limited operation, batteries, and in fuel cell, as soon as you are giving hydrogen and oxygen, they keep on continuing operation as long as fuel gas is supplied. The biggest difference between the two is that the battery stores energy, while fuel cell generates energy by converting available fuel. A fuel cell can be a battery component to store energy. Fuel cell can have a battery as a auxiliary component to store energy, but vice versa is not possible. So whenever you talk about the renewable energy technology, don't call fuel cell as a storage device. Fuel cell is a conversion device. Battery is a storage device. This is a mistake that I have seen students are making most of the time. Now I will focus on the fuel cell for a second. Fuel cell are basically harness chemical energy of hydrogen and oxygen to generate electricity without combustion or pollution, because end product is water. Now, how fuel cell works, that's the important point. And I'm right now, there are many different kinds of fuel cell, but I am going to explain the functionality of proton exchange membrane fuel cell. Now, in proton exchange membrane fuel cell, we have anode, cathode, and at anode, oxidation takes place where hydrogen is being converted into hydrogen ion and is channeled through the feed flow plates. Whereas on the cathode side, oxygen from the air is channeled to the cathode on the other side of the wall. At the anode, platinum catalyst causes the hydrogen to split into positive hydrogen and negatively charged electron. Because negatively charged electrons are not allowed to pass through the proton exchange membrane. It's only the proton that passes through the proton exchange membrane. That means the electrons, negatively charged electron has to pass through the external circuit, whereas proton has to pass through this proton exchange membrane. Similarly, at cathode, air carrying oxygen is entered, and these are the platinum coated carbon catalysts, which convert oxygen into oxide ion, which reacts with external electron and proton that is coming towards it, and the product is water. So that is the whole mechanism of proton exchange membrane fuel cell. So these are different parts of the fuel cell, as you see. This is an anode. As I already explained, this is a proton exchange membrane fuel cell, also called polymer electrolyte membrane cell. It has a different thickness and different coatings. Basically, it's a Nafion-based membrane, which only allows which is permeable to protons only. Now, I'm coming back to my previous slides. Now, since one cell produces voltage of 0.7 to 0.9 volts, so we have to arrange this electrochemical cell into stackings in a series to get the desired energy requirement. So individual fuel cells are stacked or placed in series to create sufficient voltage to meet the relevant application requirement. That's how it looks like a fuel cell. And the good thing is the battery, the fuel cell efficiency is much greater than the electric battery, so which is 40 to 60%. In European world, its trains are running on fuel cells nowadays. In Germany, even in most part of the European world. So these are basically in operation in buses or even in tested in trains in Germany. I already explained the parts of the fuel cell. Now there are different types of fuel cell depending upon the application and the temperature of operation. Proton exchange membrane fuel cell operates at 60 to 90 degrees Celsius, whereas hydrogen fuel, where hydrogen is the fuel and the other side oxygen is coming. But in case of alkaline FC fuel cell, the operating temperature is 80 degrees Celsius. Molten carbonate fuel cell has a high temperature, and solid oxide fuel cell require oxide ions to show conductivity. So the temperature requirement is quite high. So there are quite of researches going on in the field of fuel cell that people are either working to find a substitute of Nafion membrane, which is acting at a proton exchange membrane fuel cell, or people are working to replace the catalyst that converts the hydrogen into proton. Normally, people are using platinum-coated carbon electrodes. So platinum is expensive, so most of the researchers are looking for substitutes. So this is a second direction where one researcher can look to work for. And another important problem is that fuel cell scientists are facing is that to reduce the operating temperature of such a kind of cell, because at 900 degrees Celsius, you get the desired conductivity, proton conductivity, which is not, or oxide conductivity, which is not required. Such a high temperature one cannot use in application. So reducing the temperature of operation is another impediment. This is something like, I would like to focus on the Nafion a bit. When I say proton exchange membrane fuel cell, means in between the fuel cell, there is a membrane that allows proton to pass through. This is the structure of Nafion, which is perfluorosulfonic acid based membrane. So developed by DuPont, so it's very expensive. I just like to share with the audience that we have tried to import it, but we are banned. Pakistan is not even allowed to import Nafion membrane, unfortunately. So we have to find a substitute in that perspective. There are different codings. Nafion 117 means there is 1100 gram equivalent weight of membrane and 7-inch thickness, 0.007 inch in thickness. So these are different kind of membranes. If you see on the right corner, there is a perfluorosulfonic acid is basically SO3H based perfluorosulfonic membranes. SO3H means when desired temperature is obtained, the SO3H molecules start rotating, and in that way proton passes through the channels. This is a membrane. This is another membrane. These are the empty channels which are hydrated, which allows the proton to pass through. This is basically the one of the mechanism how proton passes through the membrane. I explain the mechanism in the next slide. Basically, the sulfonic acid is sulfur coordinated to oxygen atom in tetrahedral coordination, and a proton is attached to that. And there are two mechanisms. One is called vehicular mechanism, another is called bucket brigade mechanism. In bucket brigade mechanism, the rotor molecules, which are SO3H based sulfonic acid based molecules, they rotate at certain triggering temperature. I will explain the triggering temperature of these molecules. At this triggering temperature, the sulfonate atoms moves in such a way that it allows the proton to pass through the channels of the membrane. The difference between vehicular and bucket brigade mechanism is that the rotation allows the proton to pass through one by one through the neighbors. And in vehicular mechanism, it's like loading a car with a proton and allow it to pass through the channel. So these are different mechanisms explained in various papers. The molecules of interest are mostly the group in Susanna Haile. She is right now in Northwestern University in USA, but earlier she was in Caltech. I was collaborating with her on one of the projects where we have developed some rotors. These rotor molecules rotate in such a way that you see that the proton passes through the aid of these rotors. And triggering temperature, as I talked in the previous slide, is the temperature where this conductivity is shown. Proton conductivity is enhanced manifolds. And just being a crystallographer by training, I would like to explain it better in crystallographic point of view. So, for example, in this particular molecule, which is rubidium HXO4, rubidium hydrogen sulfate based molecules, here the temperature is 414 Kelvin. Below that temperature, we have a monoclinic phase, and above this temperature, we have a tetragonal phase. So 414 K is the triggering temperature where the rotation mechanism kicks off, and with the inception of rotation, as the rotor molecules get activated, we encountered a phase transition, and there are many ways to encompass or what you can say is check whether this mechanism is taking place at exactly this temperature or not. And the one of the method is to check via, simplest method is to check via differential scanning colorimetry, which is available in the lab. So you can even see kink at that particular temperature, which should be reversible. Depending, here, this is the first order phase transformation from low conducting to high conducting phase that is taking place at 414 K. I will not explain first, second, third order of Landau theory of phase transition, but I will just give you a glimpse. That's what is happening basically. If you see, as we move from monoclinic to tetragonal phase, or even to cubic phase, there is a big jump in the conductivity and accompanying the phase transition. This is an example for cesium hydrogen phosphate. That kind of transition is called superprotonic transition. That results in drastic increase in the conductivity, which is required for the operation of proton exchange membrane fuel cell. These are different kind of, on the right hand side, these are different kind of rotor molecules that are being investigated in different research groups. These are oxide-based rotor molecules, and there are also sulfide-based rotor molecules, depending upon the application. Now, this is one of my work that we published together with Professor Martin Johnson at Max Planck Institute for Solid State Research in Germany, where we have investigated these rotor molecules and mechanism. Actually, I don't call myself as expert of fuel cell or battery. I call myself as a scientist who can probe these kind of movements at atomic scale. So we have been trained in Germany not to call yourself a legend or something like this. Just call that what exactly you are doing. We have been investigating the dynamics of these rotor molecules. That doesn't mean I'm an expert in fuel cell or I'm an expert in battery. I don't know how to assemble a battery on large scale. So as a scientist, one should not claim big, one should not do big claims. This is my suggestion to students only. So at certain phase transition, what is happening actually is that we have one orthorhombic phase that is transformed into cubic phase. How can one see that? Just by single crystal X-ray diffraction. You can see these are the single crystal diffraction spots. At 400 K, these are very well refined and very well high symmetry structure, which is showing the different diffraction planes. At 298 K, there are certain systematic absences and satellite reflections, which hints that there's a phase at low temperature is different than the high temperature. So there is a phase transformation taking place. And this is a structure, single crystal structure that we have grown and solved. And these are the results. Another good thing is to see the thermal ellipsoid of the oxygen. For example, if you have metal oxygen metal bond, if the metal oxygen metal bond is vibrating or rotating, that it means that the oxygen thermal ellipsoid has to be big, will show a big ellipsoid. But when it's not rotating, it will be very well defined circle, as shown in the lowest picture left. But at high temperature, the ellipsoid gets bigger. Through the help of crystallography, one can calculate the B-ISO thermal ellipsoid, and the higher the value directly depicts that the oxygen is moving. So this is one of the methods to check. Second method, as I told you, is through DSC, right, left. So at certain temperature, the phase is cubic, above 300 and above 380 Kelvin, and below that the phase is orthorhombic. When it's cubic, then means A is equal to B is equal to C. So we have single line. But below that we have a orthorhombic phase where A is not equal to B, not equal to C, alpha is equal to beta is equal to gamma is equal to 90 degree. One should know all these things, and one should easily calculate these information from single crystal X-ray diffraction and also from powder diffraction. I will explain how one can calculate the lattice parameter from the powder diffraction and how one can say That is the temperature which is around 400 K on right top blue picture, where we have only single peak that belongs to cubic phase, and below that we have a multiple peaks that belong to orthorhombic phase. So we have decided to investigate through large scale facilities, which is basically synchrotron powder diffraction and neutron powder diffraction. Being a Pakistani, earlier I was facing difficulties to get beam time at a European beam station, but now we have an opportunity to measure our sample at Sesame beam line, which is basically Pakistan is a member of that particular beam line. Is located in Jordan. And you can just write your proposal and join our Google group. Just Google Sesame Google group. I am the moderator of that group. Just send your problem and we will try to arrange a beam line time slot for you guys if you are interested in using high scale facilities. Now, I use synchrotron powder diffraction, neutron powder diffraction techniques from Paul Schorer Institute in Switzerland, because I was privileged to be there at Max Planck. So it's not a difficult job to measure these samples via synchrotron powder diffraction. So we use the MS beam line, which has these parameters. Focus spot size is 130 micrometer into 40 micrometer. And we have used the beam energy of 8 kilo electron volt to measure our samples. Now, this is the this is a singular powder diffractogram of one particular phase of these rotor molecules. Now, I have taken the X-ray diffractogram at synchrotron beam line at a temperature of 1 degree Celsius, at a temperature interval of 1 degree Celsius. For example, the phase transition is taking place at 400 Kelvin. So means the triggering temperature is 400 Kelvin. So we have measured from 300 to 500 with a temperature interval of 1 degree Celsius. So we have a good quality data at every temperature. Now, how does it look like? Just I show you a beautiful picture, a beautiful video, just focus on that. You will see these small reflections will disappear at certain transition temperature. This is moving right now. As you can see, this is a video. Now, the temperature at which these rotor molecules start functioning is the temperature where the phase transformation is taking place. Now, it's a very well resolved pattern, as you can see in the slide. This directly depicts that the phase transformation is taking place, and on the top there is a number of diffractogram that I used for the generation of that picture using powder 3D software of Robert Denevier. Oh, very sorry, what happened? I don't know. Okay. Hello, do you listen me?
Yes, accept your sound is
Hello.
coming, but no view. You have to share screen again.
Okay. I'm lost somewhere. I don't know where to. Just give me a second. Share screen. Okay.
Yes, yes, please.
No, it's coming. Yes, yes. Okay. Now you are.
Yes, now it's fine. Yes,
okay, I'm going to
it's
finish.
fine.
Apologies. Okay, now. The another technique to measure these rotor mechanism is neutron powder diffraction, because we are looking at the oxygen rotation. The contrast of seeing oxygen via neutron is better than X-ray diffraction, because of the neutron coherent scattering length B for oxygen is better in neutron than the X-ray thing. So we use neutron spallation sources, where I don't want to explain neutron spallation sources. So you can see that in order to refine these movement of metal oxygen metal bond, we have clearly resolved the oxygen positions. What we have done is in X-ray we cannot see these rings, donuts. So we have we split the oxygen atomic position into 15 subatomic positions with the angle between the neighboring position of 24. So 24 into 15 is 360. So we have split the particular oxygen position atomic coordinates which are showing these movements. And then we have refined again the neutron powder diffractogram. And then we were able to see these minute rotation mechanisms by neutron powder diffraction. Another important thing that neutron is giving us additional features of magnetic bragg peak, which was not seen in the X-ray diffraction. So we get additional information of the magnetic nature of these molecules, which show magnetic movement below 1000 Kelvin and above 1000 Kelvin. So these are antiferromagnetically ordered materials. I will show in the next slide, and these are magnetically ordered till 1000 Kelvin. So very highly ordered antiferromagnetic with a high Néel temperature of 1000 Kelvin. This is temperature of these three molecules, I was a movement that gets stable, that remains stable in a high magnetic state till 1000 Kelvin, and above that they get disordered or paramagnetic. So now these are magnetic moment directions. I will now give you another important application. I've talked about the fuel cell, how proton exchange membrane fuel cell work, and what is the mechanism of rotor molecules within the proton exchange membranes fuel cell, and how proton starts conducting. But another good application that after J.B. Goodenough from USA, who got a Nobel Prize recently, they have developed lithium cobalt oxide as a cathode material, and they have done a lot of research in that particular direction. But recently, in past decades, people are looking for a substitute of lithium batteries, where we have a solid electrolyte instead of liquid electrolyte. You might have seen that the battery burst and the mobile phone burst into and got fired. So in order to remove it, we have to replace a liquid electrolyte within the battery by a solid electrolyte. And if you have a solid electrolyte, the major impediment is how to have a good lithium-ion conductivity using solid electrolyte. So rotor molecule has a big role to play in these solid state electrolyte lithium-ion batteries. All solid state electrolyte lithium-ion batteries where we don't have any liquid. So electrolyte is solid state electrolyte. These are the materials in the lower corner which have been extensively used. In these materials, we have a lithium lipon, phosphorus oxynitride based materials. We have garnets, we have sulfide based electrolytes, and so on. And acetone is a very famous material for that particular application, and perovskite based solid state electrolyte battery materials. So for example, take the sulfide based electrolytes. You have a PS4 tetrahedra in this Li10G P2S2, which shows a conductivity of 10⁻⁻2 Siemens per centimeter. So they are showing a very high conductivity. The mechanism is that the PS4 tetrahedra rotates the way I've shown in the previous slides, and with the rotation of these PS4 tetrahedra at particular triggering temperature triggers the conductivity of lithium to manifolds. Without the help of these rotor molecules, the solid state electrolyte batteries were not possible. So people are trying to find different substitutes, dopants, and so on and so forth. For example, they are using different dopants to enhance the conductivity, and so on and so forth. Because I'm talking about the dopants, so I will just, due to time constraints, I will just, for students, when you are selecting a dopant, you have to keep into consideration the Hume-Rothery rule. Then when if you are LiFeO2 material, for example, then if you want to put a gallium in it, it's an ideal dopant because it has ionic radii in the similar range. In iron, the ionic radii is 0.49. In the gallium, if you want to use it as a dopant, it has a 0.47. Another thing is oxidation state. They both have the similar valence state, +3, and this is another prerequisite to use a dopant. And another important thing is crystal structure. I'm a crystallographer, so if you are using orthorhombic structure, you cannot use gallium oxide directly to put inside for replacing the iron, because gallium oxide has a different structure. Iron has a lithium iron oxide has a different structure. So gallium will not leave all the crystallographic picture and just come out and sit the iron side. It has to be similarity. There has to be similarity in structure. There has to be not a big difference in electronegativity, because electronic cloud will then totally shuffles. These parameters has to be taken into consideration also for magnetism people. When you are replacing europium or highly magnetic moment materials, gadolinium and so on, then you have to keep these constraints into mind while selecting proper dopants for proper material to achieve the desired properties. How XRD shows these changes. Quick 2 slides and then I will finish maybe. For example, you are putting gallium into iron. Whether it has hit the proper atomic site or not, you have to see the shift in the photodiaphragmogram. You have a KFeO2, which is red. You have potassium gallium oxide, which is black. So green is the doped potassium ferrite doped with gallium, so which is exactly line in between the two. I've been using Topaz and other softwares for refinement of the photodiaphragmogram. So you have to refine the iron and gallium position in such a way that 1 minus atomic position of gallium should be equal to because if you replace iron with gallium, so if it is going to be doped 10%, then we have a occupancy of 90% iron and occupancy of 10% gallium. that has to be the end result of that refinement. For example, here we are in one of the research with Professor Khurshid Hasnan, I replaced strontium with bismuth, and then they were 50-50. And if you refine that particular atomic positions, then you can say exactly how much bismuth is there inside the strontium. These are the refinement end results. It has to be reproducibly the same result when you finish the refinement. And that's oxygen vacancies were also generated, as you can see, 0.91. If it would not have been replaced or doped, then it should be 1. Like iron, this particular position of iron was not doped. Only this particular position of strontium and bismuth were replaced with each other. This is the codes to do the refinements, and these are the final results. Due to time constraints, it's already people are waiting for lunch, so I would like to finish it now. I thank you all for your kind invitation and for listening to my talk. Thank you very much.
Thank you very much, Dr. Sir, for such an informative talk. And thanks for giving opportunity to LCWU. The fuel cells is very emerging field, and one of our faculty member, Dr. Munazza Mohsin, is working on it. She has done her PhD from Austria. She will be happy to see your work as well, and all the other faculty members and students as well. Thank you very much.
Thank you, Professor.
Any question from Dr. Naveed Zafar?
Sir, ma'am, I have a question.
Yes.
Can nanotechnology help us to replace the Neptune membrane, as it is very expensive and we can't use in Pakistan? So,
yes, yes, indeed. This is one of the most important research direction to replace Neptune membrane, which is basically polymer electrolyte membrane, organic polymer electrolyte membrane with inorganic solid electrolyte membrane. What you can use it, you use cesium hydrogen sulfate, cesium hydrogen phosphate, cesium hydrogen germanates, and so on. There are many list of materials which can be made composite with the respective polymer. And since I explained that if you use these material instead of perfluorosulfonic acid, which is the backbone of Neptune membrane, you may likely get the same proton conductivity or nearby. So this is the direction to work on. It's likely.
Thank you, sir. Thank you.
Any other question? If there is no other question, then I should say thank to Dr. Naveed Zafar. Thank for joining our webinar, and we will also look forward to see you in coming webinars as well.
My pleasure, Dr. Zara. Thanks for the invitation once again. Allah Hafiz.
Thank you very much. Allah Hafiz. Now our last speaker, Dr. Ghulam Nabi. Dr. Ghulam Nabi is working as assistant professor in University of Gujarat. He has published almost 100 research articles in well-reputed international journals with more than 300 impact factor. Dr. Ghulam Nabi has won numerous international awards along with 2 NRPU competitive research grants from HEC and 2 from international agencies. Dr. Sir, please start your talk. Dr. Ghulam Nabi, are you with us? Yes, he's with us.
Hello. Madam, can you hear me, please?
Yes, please. Yes, we can hear you. Then again, your sound.
Hello.
Yes, please. Dr. Ghulam, maybe some internet issue because your sound is not coming. Your microphone is off, but we are getting here a sign of your microphone is coming off.
Hello.
Yes.
Can you hear me?
Yes, now your sound is coming. Dr. Ghulam Nabi, you will have 15 minutes to sum up your talk, please.
Hello, please, can you see my slides?
Yes, your slides are visible now. Do the slideshow.
Thank you very much, Dr. Zohra Nazir. I am very thankful to the organizers for giving me a chance here to present my work. Not only my work, actually, I am also representing my group in the University of Gujarat. Today I have honor to deliver a talk about the two-dimensional hexagonal nanosheets as potential nanostructures for energy storage devices. Before my talk, it was also about the energy storing system, just like the fuel cells. But here in my talk, I will discuss about different energy storing devices. Before I go to my talk, I would like to share some of the views of my university. If you go to Islamabad from Lahore, then on the midway you can see the beautiful view of Gujarat city. It's called Babe Gujarat, and then you can come to the University of Gujarat. It's the aerial view of University of Gujarat. Actually, it's a little bit old picture. Now it's almost all green area. These are the academics blocks. Actually, it's a very beautiful architecture that has been made purely on the university basis. Along with the infrastructure, we have numerous experimental and characterization facilities here. Later, if some colleague or some student want to take help or want to collaborate, they can just visit us or just can share by email. We have in our university a chemical vapor deposition technique, which is a very sophisticated technique for growth of the nanostructures. And we are using hydrothermal method, which is also a very common method, sputtering method. And we have an electrochemical workstation, which we have recently bought from USA. It's Gamma 5000E. And then we have a fluorescent spectrophotometer and UV visible spectrophotometer. These facilities we have in our lab in University of Gujarat, Department of Physics. Along with these facilities, we have also laser setup, which unfortunately is not working right now. Raman spectroscopy we have also, but we have also another Raman spectroscopy in nanobiotechnology group here. And we have photocatalytic reactor, which is used for the photocatalysis. So if we want to use these facilities, first of all, we should go to the nanomaterials. So nanomaterials are the materials which have a dimension, usually 1 to 100 nanometer. And most of the researchers know that if the dimension of the material changes, its properties dramatically changes. Just like if we take the simple example of wood, we have bigger blocks, and if we make it sheets or just we make it stuff, and if we want to burn it, so it's very easy to burn the smaller particles. So if we want to burn the block, it's a little bit difficult to burn at the start one. So we can see if we take simple example of wood. So if we just change its size, so it has different properties. Usually in nanotechnology, we have different types of nanostructures, just like the zero-dimensional nanostructures, one-dimensional nanostructures, two-dimensional nanostructures, and three-dimensional nanostructures. I will just give overview of these materials, but I will just focus on the two-dimensional nanostructures. Zero-dimensional nanostructures are usually quantum dots having size less than 1 nanometer, and then we have their band gap, and which can be tuned for different color systems. Along with the zero dimension, we have one dimension nanostructures, which are in the forms of nanotubes or nanorods or nanowires. Here are the some of the examples or some of pictures of one-dimensional nanostructures. One-dimensional nanostructures can also be in random form, just like this one, and it can also be in the form of regular arrays. Along with this one, we have also two-dimensional nanostructures. One of the best example is graphene, which is in the form of the sheets. Along with this one, we have also hexagonal nanosheets, or we have also nanobelts. So this kind of nanostructures can also be used potentially for devices fabrications. If we just want to learn how two-dimensional materials are prepared, so if we just take the tube and rupture its one side, so we can convert this nanotube into the two-dimensional nanosheet as shown in here in the diagram. But if we go to the three-dimensional structures, it may be a bulk material, or you can say it's a combination of one-dimensional nanostructures. Just like this one, you can see here, it's one-dimensional nanotubes. But if we combine these nanotubes, so we can just prepare three-dimensional nanostructures. Just like this one, 3D nanotube structures, and these structures have x-axis, y-axis, and z-axis. So actually, its basic unit is also nanotube or one-dimensional. But if we combine these one, so we can convert these into the three-dimensional nanostructures. These are also some examples of the nanostructures which are 3D, which has been grown by CVD or etching method. So if we go to the these nanostructures, so basic purpose is why we grow these kind of nanostructures, and what is their basic aim. And then if we have some specific purpose, which synthetic techniques can be used to synthesize such structures, and later how these nanostructures can be used as a devices applications. Nowadays, everyone is familiar about the television, laptops, cell phones, or hybrid auto vehicles. We can use these nanostructures in these utilizations. But if we especially go to the laptops or cell phones, we have some specific requirements. Before I go to the requirements used for the cell phones or computers or laptops, here is very interesting one or two examples of the nanostructures applications. We have a thermochromic sheet, which can be used to detect the temperature of the body. It's actually thermochromic sheet, and if you even touch this one, and by touching its variation in temperature can detected by this thermochromic sheet, and it can give the range of the temperature which have this sheet or your body. Along with this one, you can use this one as smart fabrics. Now are being used in most of the countries. Same cloth can be used for the winter season and also for the hot season. So if we use the laptop, or even we go to buy a cell phone, so usually we just ask one first question from the shopkeeper or just one friend, how long its battery will last. I mean, if we buy a laptop, so we definitely concerned about its battery timing, or even if we buy a cell phone, then we will also have concern about the its battery timing. So battery timing is a major issue nowadays, which can be solved in many ways. So when we just see, we can see just this one, how long it will take to discharge, and then even we also need to know how long it will use to take the charging one. I mean, we need longer battery life, and we also need the short charging time. Along with this, laptops or cell phones, nowadays hybrid vehicles are also being used in advanced countries, where especially Tesla has made a great improvement. So they can use the electric vehicles for the transportation. And in these electric vehicles, they are using batteries as well as supercapacitors. But for the transportation, actually, these are the huge buses. So we need more power for the utilization of these materials as a supercapacitor. Just if we go to next slide, we have in this slide we have different types of devices which are being used. We have fuel cells, conventional batteries, supercapacitors, and conventional capacitors. Actually, batteries have very high energy density, but they have lower power density. For supercapacitors, they have a high power density, but they have a lower energy density. So if we want to use the supercapacitors, actually they have already high power density. So our purpose is to increase its energy density. So our main purpose is to go to the index direction shown here. Actually, we want the energy storing devices which have high energy storage and high. So along with the high power density and high energy density, we also concern about their charging. So for this kind of structure, we need two-dimensional structure, which have high density and high conductivity, just like the graphene, and it would have flexibility and unbreakable. So if we have this structure, we can do it efficiently, and this can be used in
नमाज पढ़ो अर्जन
and
अर्जम
and even we can use in the smartphones and auto vehicles. So now, how to develop novel, controlled, and reliable routes for nanostructure devices application? If we want to nanostructure for these kind of devices, so how we can develop these nanostructures? So we have basically used two types of techniques, chemical vapor deposition, and we have used hydrothermal method. This is the actual image of the chemical vapor deposition structure, or you can say the horizontal tube furnace, which is being used for the chemical vapor deposition. And here is the schematic diagram. We can just take a tube and silicon substrate or any other substrate, and then we just heat it up and give some kind of flow, so we can take some we can get some nanostructures. Here is the basic mechanism. When we give the heating and also gas inlet, mass transportation of these materials occurs and reaction occurs. And after that reaction, this diffuses on the substrate. We can grow substrate nanosheets, or we can grow even the nanowires. And at the surface of the substrate, these interacts and desorption by the products, and then we can get the nanostructures, and the remaining residues can be removed from the pump. So this is a basic mechanism which is being used by CVD method for synthesis of the nanostructures or nanosheets. The other method is hydrothermal method, which is also a very common method. We can just take a solution of some precursors and then put it into the autoclave and heat it up, and we can get the desired results. Specific example, if we take the specific example, we have synthesized cobalt hydroxide and vanadium doped cobalt hydroxide for the application of the supercapacitor. Here is the block diagram for the synthesis of the nanosheets, and here you can see the nanosheets in the diagram A and B and C. The nanosheets are not very clear, and if we increase the concentration of vanadium, then we can get the purely hexagonal nanosheets, which are being used for the supercapacitor electrode applications. Here is the Tmt image for the confirmation that the hexagonal nanosheets have been prepared accurately. So here is a electrochemical analysis of these materials. In the A, we have used the pure one, and B, C, and D, we have used 5%, 10%, and 15% vanadium doped cobalt hydroxide. So we can see here that if we increase the concentration of the vanadium, then the specific capacitance of the cobalt hydroxide can be increased. Similarly, if we increase the scan rate, with the scan rate, the specific capacitance is decreases. Here is the two-dimensional nanostructures, and we can see here the cyclic consistency. Actually, for the cyclic consistency, if we use any material, then we that material should be very stable. So if the stability of the material is not good, so that cannot be used for the supercapacitor. So here we can you can see we have used it for the 2500 cycles, and its capacitance retention is 89%, which is good enough for utilization of the supercapacitors. Here is the Nyquist graph or impedance. From the impedance, we can also see that the 15% vanadium doped cobalt has the less resistance, which is useful for the supercapacitors. Along with the supercapacitor, here is actually the comparison of the vanadium doped cobalt hydroxide with the other materials, which is almost 2 times greater than that of the other prepared materials. Along with the supercapacitor, we have on other technology, which is called the hydrogen storage technology, which is also being used for the hydrogen energy. Hydrogen is also a very more abundant and have a clean energy features, which is being used in fuel cells and vehicles, and also used in drones, and also in the space shuttle. We have synthesized these type of porous nanosheets for the hydrogen storage purpose. Here you can see the hydrogen storage curves. We have absorption curve in the red form, and after the absorption, we have also dissolved this one, and this is blue one is the desorption curve for the hydrogen storage. So we can see such kind of nanosheets can be used effectively for the absorption and desorption purpose. The size of these nanosheets is actually a little bit bigger one. So we, after changing some conditions, we are also able to synthesize some nanosheets with a thinner size or a smaller size. You can see here, these are also perfectly hexagonal nanosheets and can be grown by CVD method. We have used these nano sheets for the hydrogen storage also. These are some of the characterization techniques, which this is showing the pure gallium nitride, and this is also the XRT, TEM, and HRTM image, which is consistent with the standard data. So it means the prepared nanomaterials or nanosheets are of pure form. Here you can see we have also studied the effect of temperature on the absorption of the hydrogen. So here you can see the graph at 100 centigrade, 200 centigrade, and 300 centigrade. You can see clearly the increase of...
Dr. Saab, kindly try to conclude your talk.
just madam, I have just one two slide more. It's already
Okay, fine.
so it's so we can say with the increase of the temperature, the absorption of the hydrogen can be increased. Here is some of the comparison which we have used. You can see in this class, the prepared material have the highest energy hydrogen storage, which is which can be used for the energy systems. Here is a little bit mechanism about the absorption system, in which we can see that at different places, or you can say the gallium places, gallium vacancy places, 1, 2, or 3 hydrogen atoms can be stored. How we can see that these are stored at the gallium vacancies? For this purpose, we have photoluminescence properties, in which we can see that at 367 it has a band edge emission, and at 553 nanometer it's actually the P for the gallium vacancies. So these gallium vacancies show that these kind of nanosheets have enough space for the storage of the hydrogen. And these can also be used as the yellow LEDs, because its recombination occur at 553 nanometer, which lies in the yellow region. So here is the last diagram, which is shown that we have actually measured the photoluminescence before the absorption and after the absorption. Blue one is as in size, and when we measure its photoluminescence after the absorption of hydrogen, so you can see its peak intensity has been reduced, which is an evidence that hydrogen was absorbed in the system, and the lower intensity is due to the some of the residuals which has been remained in the system. So these kind of nanostructures can be effectively used for the hydrogen storage, absorption and resorption mechanism, and also for the energy storage in supercapacitors. So these kind of nanostructures can be effectively used to meet the energy requirements. Thank you very much.
Thanks, Dr. Ghulam Nabi, for a good talk. Any question, audience, if you want to ask? One or two very quick question. Okay, then thanks a lot for joining our webinar. Actually, we are running short of time. So we will quickly move to our next and last entity, that is the e-poster presentation. Because a lot of students from LCWU and from the other universities have participated in the e-poster competition. Today we will display the half of the poster, and rest half will be displayed on the next day. So we are moving to the poster displays. with these e-poster presentation, we are now at the end of our today proceedings. Thank you very much for joining the webinar. E-poster presenter must be waiting for the results, and tomorrow, inshallah, at 12:30, we will announce your e-poster results. Actually, today we consume more time because in the morning our 3 senior professors were here and they were discussing very important things which were beneficial for all of us, for all faculty and for all students. So that's why there is some lapse in time as well. Tomorrow, inshallah ta'ala, we will see you again on this forum. Thanks, and thanks for participating in this webinar. Yes, Dr. Akram, you want to ask something? Dr. Akram Azhar?
Assalamu alaikum, ma'am.
Walaikum salam. How are you,
Ma'am, I'm
Dr.
sorry. अल्हम्दुलिल्लाह वो ना ऑफ हो गया था नेट, तो मैंने अभी इमरजेंसी में दूसरा नेट लगाया है, तो इसलिए मेरा पोस्टर का टाइम था शायद आज।
जी वो डिस्प्ले में गुजर गया आपका पोस्टर, कल दोबारा कर दें डिस्प्ले उसको?
जी प्लीज प्लीज प्लीज।
ओके फाइन, दोबारा कल कर देंगे आपका, ठीक है ठीक है।
थैंक यू मैम, थैंक यू।
ओके, यू आर वेलकम। ओके देन इट्स टाइम टू से गुड बाय। Nice to see such good speakers from Pakistan and abroad, as well as our students and other participants. Thank you very much. Inshallah, tomorrow we will start a webinar at 10 o'clock. Allah Hafiz.
Allah Hafiz.